All right. Just checking if the mics work. I think they do. Yeah. All right. So, given that we're 2 minutes away from the official start time, I thought, we could quickly take a few moments and welcome everyone. So, thank you for coming. Some people from very far away, some people from London, but, that's the beauty about having RAS meetings. You get to meet people that you often don't get to see when you go and visit, across the UK. But yeah, so today we've got a very specialist discussion meeting planned. And the key aim behind the meeting when we actually proposed this to the RAS was to bring together experts in theory and observations, low redshifts, high redshifts, local universe, galactic people, to really come together and, brainstorm all of these exciting results that we've been finding in the area of JWST particularly, but also from, simulations and all of the exciting physics that, people are really pushing the envelope towards. So yeah, this is very much meant to be an interdisciplinary, bringing together a whole group of experts together and, brainstorming ideas for future collaborations, but also learning about, what the coolest things are out there in terms of amazing research. So my name is Ayush and this is Alex, and we'll be the organizers today. So I think without further ado, we've just hit the half-past mark. So the first speaker of today is going to be Elizabeth Stanway from University of Warwick, who'll give us an invited review on, population synthesis and IMF. So take it away.
Okay, hello everyone. I hope everyone can hear me. I will be giving a bit of an introduction. It will probably start quite basic, and that's because this is a meeting which combines expertise in lots of related and interdependent, but nonetheless quite independent areas. And some of us are more senior, some of us are more junior, so I'm not deliberately trying to be patronizing, although I will probably come across that way occasionally. In fact, I'm going to start with the most patronizing statement I am going to make, which is that galaxies are made of stars. It's amazing how many people do not take this into account. That means we need to understand stars, stellar evolution, the impact stars have on their surroundings before we understand the galaxies. And that's crucial. Most of the time looking at galaxies, we're looking at integrated light, or perhaps light integrated on tens or hundreds of parsecs or kiloparsec scales. And we're not looking star by star. So we need to compare this to models to understand the stellar population. The dominant form of model that is used for this is known as a population and spectral synthesis model. So just to give everybody a reminder or a quick primer on this, this starts from the assumption that we have a reasonable grasp of how individual stars evolve as a function of mass. We can model how a sun-like star evolves, how a main sequence or post-main sequence star evolves over time. We can then combine those with an initial mass function, on which I will say more later, which tells us how many stars we have of each kind. And we can look at how the integrated light of the population or the composition of the population changes over time. So if we just look at the composition, this is population synthesis, we can look at the ratios of different stellar types. We can look at things like HR diagrams. We can look at transient rates, because if we're modeling how stars live, we are also modeling how stars die. And this is very relevant for a lot of studies these days, which are using events like gravitational waves or gamma ray bursts to model stellar populations. We then have to go through an additional step if we want to compare them to galaxies, and that is spectral synthesis. This is where we take our information on the luminosity, mass, temperature of a star as a function of age, combine it with a spectrum, either taken observationally or theoretically, in order to make a composite spectrum that we can then compare to the integrated light from a stellar population. This will give us photometric colors, spectral information in the form of absorption and emission lines, and things like the color magnitude HR diagram, as opposed to the theoretical one. So this isn't a new idea. SPS models have actually been around a surprisingly long way, and their concept can actually be traced back to Beatrice Tinsley, a New Zealand American astronomer who in 1967 wrote her PhD thesis on the premise that if you took 13 stars with information about how they evolved at giga-year intervals and combined them, you could learn stuff about galaxies. Now, we've come a long way away from 13 stars. These days, a population synthesis model will often have hundreds or possibly even thousands of stellar evolution models going into it. But the general idea is still the same. You take a population of coeval stars, stars that formed at the same time, you distribute them in mass according to an IMF, and you build a composite spectrum or evolve the population and then build a composite spectrum. The output is what's called a simple stellar population if it starts with all populations of the same age, and then can be combined with a star formation history to become a composite or complex stellar population, a CSP. We're as guilty of three-letter acronyms as anybody else. You've got SPS, SSP, CSP, but we try and build them logically, one from the other. You can go a step further. What I've described is the first row of this diagram, which comes from a review by Charlie Conroy, where you take the IMF, the stellar evolution models, and the spectra, and you combine them. If you then combine it further with a star formation history, a chemical evolution history, and information about dust emission and absorption and nebula gas, you can make a full synthetic spectral energy distribution. And that's what you really need in order to compare to galaxies. So leading SPS codes, by which I mean codes with spectroscopy, include things like GalexEV, Starburst 99, FSPS, that's Charlie Conroy's models. The Marston models, I've written down 2005 and 2014, but they continue. We'll hear about one of the most recent iterations of that later today. And all of these primarily use single star, isolated star evolution. Okay, some of them are making movements towards binary pop synth, but in general, they're built on stellar evolution models that assume that each star evolves in isolation from its neighbors. And that's an issue because we know that most stars in the universe are not isolated. In fact, if we look at massive stars which dominate the light from the distant universe or star-forming galaxies, or which dominate metal production, for example, in many elements, then we're looking at these systems here, which have a binary fraction or tertiary fraction, a companion frequency that exceeds 1. Okay, you're more likely to find one of these massive stars in a triple than you are to find it in a single star. Now, by the time you go down to about 1 solar mass, the population that gives rise to white dwarfs, for example, you're looking at maybe 20% of the population in binaries. But that shows a strong evolution with metallicity. So even if we're in the distant universe, where we expect the metallicity to be low, even solar mass stars are going to be showing a high binary fraction. And this is going to have impacts because the spectra of these young stellar populations are dominated by the most massive stars. Hugh Sarna, back in 2012, 2014, estimated that 70% of massive stars will not just have a companion, but will interact with it during their lifetime. The numbers here change up and down, and we will hear more later about more recent attempts to evaluate the impact of massive star binarity and other parameters. But the effects of many of these interactions, mass transfer, stripping, and so forth, are often strongest at low metallicities. What this means is we really cannot ignore the impact of binaries on emission line galaxies. So what do you have to do to include binaries? Well, I'm not going to go through this in detail, but we've taken our core of stellar population synthesis, and we've added a lot more physics. We now have to worry about rejuvenation, mixing, stripping, common envelope evolution. And where before we had one stellar evolution track per mass, Now we need an evolution track per mass, per companion mass, and companion initial period. Okay, so we're going from thousands of stellar evolution models in a synthesis to hundreds of thousands of stellar evolution models in a synthesis. That means we also need additional input parameters. We need to know, for example, the initial period and mass ratio distribution. And we're going to find some of our stars ending up in regions of parameter space that single star evolution just doesn't reach. Strip stars, Wolf-Rayet-like hot subdwarf type stars are going to give you different atmospheres, different temperatures, different atmospheric compositions to those we typically see in a single star population. So you need to include those. But the benefit is that because you've put a lot more physics in, you can also get a lot more physics out. And there are some observations in the universe which are fundamentally binary in nature. Type 1a supernovae, gravitational wave compact object mergers, for example. These are events that simply cannot happen without binaries. And we know that the stellar population is binary rich at low metallicities and for massive stars. Okay. Now, the relative importance of the different impacts we can still argue about, but I don't think anybody argues that there will be impacts of some kind. So binary population synthesis, it's still a smaller field than standard star population synthesis. Many of the codes have focused on the population synthesis step because they're primarily designed to establish things like transient rates. Okay, for this, you can use the BSE equations of Hurley et al. You could use codes like Star Trek or Seven or Poseidon. But to compare with a galaxy, you've then got to take those outputs, combine them with spectra. And the most established of the spectral pop synth codes is BPAS. There are one or two others which are making steps in that direction, but generally have binarity as a limited input to their models. Okay, so a great deal of progress has been made in SPS models, certainly since the 1960s, but even in the last decade, there has been a lot more effort put into modeling the stellar evolution and the stellar atmospheres and understanding the impacts of different uncertainties in these parameters. So we can ask the question, is stellar population and spectral synthesis a solved problem? Well, it won't surprise anybody that I'm going to say no. If I said yes, I'd be arguing for you not funding my next postdoc, which is not what I'm trying to do. So where are there still big uncertainties on the SPS side? Well, you can ask questions about what stellar evolution models you are using. This is the fundamental input to SPS codes. And they really fall into two broad categories. There are what are called the detailed models. These solve the interior structure of the star iteratively at every time step. And they're very slow. It can take half an hour to calculate a single star. I've already told you we need hundreds of thousands of stars, so this can be an issue. Or you can go the other way and look at what's called rapid models. Now, these use a small grid of detailed models to tune an analytic approximation to the evolution. It works really well in some regions of parameter space. Single stars in kind of normal mass ranges, normal main sequence stars, very easy to model analytically. Once you start throwing in binary interactions and how the binary structure responds to mass transfer, then a lot of these approximations can't really follow the details of what's going on. So they are much faster. That means you can vary more of the physics using these analytic approximations. But in some places, some regions of parameter space, they're less accurate. So a lot depends on what you're using your population for. If you're using it to evaluate observational data in a safe region of parameter space, rapid models are great. If you're using it in a region of parameter space which has a sensitive dependence on binary interactions, then it can be more challenging to apply these models. So that's the stellar population model step. There's also uncertainties on the stellar spectral libraries you use. These three plots from a paper by my postdoc, Connor Byrne, show the different spectra that different spectral libraries would give you if you ask for a star at fixed composition, temperature, and gravity. Okay? And again, you can see that there are some regions of parameter space where everybody agrees what a spectrum looks like. Pretty much everybody agrees what a B star at kind of main sequence type gravities looks like. That's the middle panel in the optical. Pretty much everybody disagrees about what a cool star looks like in the optical. And once you get out into the ultraviolet, almost anything could be happening. Now, recent projects like Ulysses and associated ultraviolet spectroscopy programs are working really hard to improve our estimates of what's going on there. But the large spectral grids you need to do a stellar population synthesis are still somewhat limited once you go beyond the optical in either direction, or when you push the limits of parameter space. You could argue for using empirical spectra. These are the spectrum of an observed star, and it will often have features in it that you can't explain from its fundamental physics. So it can be quite hard to know, is this the correct spectrum to assign to my stellar evolution model? Alternatively, you could go with theoretical models. These you've built from first principles, so you know they match the physics of your model, but they're probably missing some information in their line lists, some information in their spectrum, and some of the numerical approximations that are made in order to calculate an atmosphere model. So there are pros and cons both ways. You also have to worry about whether your star is in local thermal equilibrium, like a main sequence, a nice medium mass star like the Sun, or whether it's one of these stars that is almost on the point of blowing itself apart. Most massive and very massive stars have wind speeds which are close to the Eddington factor. Well, these stars are on the point of blowing themselves apart. But there were other people here today who know more about that than me and will probably tell us more on that side. So you do have to question whether your spectral grid that you are applying is appropriate to the dominant stellar populations which are feeding into your features. You also have to worry about binary parameter distributions. Most of these are calibrated in the very local universe, most of them in the Milky Way. Examples here in the plots. The points show the estimates of companion frequency from a review by Mo and Di Stefano in 2017. And you can see that the error bars are quite large. All of the grey lines here are plausible distributions sampled from the posterior defined by those error bars. And you can see that the fraction of companions you have as a function of period, as a function of mass, and as a function of mass ratio, all have uncertainties. They all have uncertainties in the Milky Way. They have even more uncertainties when you extrapolate to low metallicities. And we will almost certainly hear more later about recent work that is ongoing to try and constrain these at lower metallicities, in particular from the Bloom team, although I have no idea if that's how you're meant to pronounce that word. So you also have to worry about an additional parameter, which is nebula gas and dust. Okay, we're looking at star-forming galaxies. We can model their stars, and okay, I've probably undermined your confidence in our ability to do that already, but there's a whole nother layer. Before the light from the stars gets to us, it has to pass through the birth clouds, the interstellar medium, the circumstellar medium associated with those star-forming regions. This absorbs away blue light, it produces nebula continuum and line emission and far infrared emission from the dust. And so you have to model that, and that introduces a whole additional set of parameters to worry about: gas density, ionizing spectrum, composition, ionization parameter, dust curves, okay? But for that sort of thing, usually you'd take the output of an SPS code and use it as the input to a specialist code, such as Cloudy or mappings, that is designed to do this form of radiative transfer. Now, the other big uncertainty, and for one which is going to form the focus of a fair amount of today, is to do with these initial functions, these initial mass functions that we are assuming. Now, before I talk a little bit about initial mass functions, it's always important to get your definitions right, because people use the term mass function very loosely. Some of us will use it to describe galaxy mass functions, some stellar cluster mass functions. Where people talk about the stellar IMF, broadly speaking, they are talking about the distribution of stellar masses that is expected to form from the collapse and fragmentation of a single giant molecular cloud. Okay, now that is not going to be the same as the present day stellar mass function, which could have been modified by massive stars living and dying, or low mass stars being ejected from the region, or a host of other dynamical effects. And it may well be different to what's known as the filled star IMF, which appears steeper, largely because it may well have a strong contribution from low mass companions kicked out of denser regions. So it looks as if you have relatively fewer massive stars compared to low mass stars. So when you're looking at a mass function, you do have to think a little bit about which mass function you're looking at and what has happened to modify it. One of the things that can modify it, for example, is the size of your stellar cluster. If you have 100 solar masses of stars being formed, the chances of all of those ending up in one 100 solar mass star are very low. So there's a strong reason to suspect that the most massive star in a cluster will scale with cluster mass. Okay, that means that if you're going to compare to a galaxy, you might also need to think about the cluster mass function as well as the stellar mass function for each cluster. And this is what underlies what's called galaxy-wide IMFs, or the integrated galaxy IMF theory that Pavel Krupa and collaborators have been working on. So let's go back to the fundamentals for IMF. This is the fundamental. This is the Salpeter IMF function of 1955. The 3 points in the middle show how it has been normalized to fit globular cluster data in the local universe. And it suggested that the number of stars of a given mass scaled as a simple power law with the mass of the star in the range from about 1 solar mass to about 100 solar masses. Okay. We now know with a high degree of confidence that at the low mass end, the Salpeter law massively overpredicts. So the dark blue line here that has high mass numbers at high numbers of stars at low masses is the original Salpeter law. It's now firmly established from the Milky Way that there needs to be some kind of turnover. How you turn over depends on who you talk to. A point of clarification here, people often get confused between a prescription which uses alpha for your IMF power law index, that's if you're looking at number as a function of mass, or gamma, which is the number as a function of log mass. Now, people do use alpha and gamma almost interchangeably, but they differ by 1. So a Salpeter slope can either be minus 2.35 or minus 1.35. It's important to know which one you are actually using. I'd also say that definitions of terms like top heavy, bottom light also vary. If you talk to someone who works on elliptical galaxies, then a population rich in 2 solar mass stars would be top heavy. Okay, if you talk to somebody in the distant universe, a population rich in 100 solar mass stars would be top heavy. So these are ambiguous terms, and you should always define them if you are using them. But we still have questions about the IMF. So we can ask, what is the true slope? Salpeter suggested minus 2.35, and we still use that in the vast majority of cases. But it's almost certainly slightly steeper or slightly shallower, depending on where you're looking. We can ask, what about massive stars? Even if you know what stars between 1 and 100 solar masses are doing, can you have 100, 150, 200, 300, 500 solar mass stars? Okay. And if you do have them, how many do you have? And does that distribute as a power law, or do you have to count them individually? Are you ever going to make more than one 500 solar mass star in a cluster? Okay, if you have one 200 solar mass star, will that suppress anything more than 100, anything else more than 100 from forming? When we're weighting statistically, we're assuming we can have 0.1 of a 200 solar mass star. That may not sound like a big problem, but these very massive stars are so luminous that having 1 or 0 significantly impacts the output spectrum. And there's a strong argument for counting them stochastically. And as I mentioned, there's the low mass turnover. Now, those of us working in the distant universe may think the low mass stars are less important than the high mass ionizing stars, but this will have big impacts on your mass estimates. For a salpeter like IMF, the average mass of stars is actually 0.6 to 0.8 solar masses, depending on where you put your turnover. So the majority of the mass is down at this end, and the shape of your turnover will affect your mass to light ratios and thus your inferred masses from SED fitting. Now, just to show you the level of uncertainty and confusion in these, this is a compilation from an annual review published last year of the measured values for the IMF slope as a function of stellar mass. And you can see even in the regime we would usually describe as being salpeter between 1 and 100, you've got pretty much a unit scatter in measurements. Okay. Note also how large these error bars are. Even in the local universe, it is really hard to measure the IMF of stars directly. We could put some additional points on here. We could point out the very influential result from the Tarantula Nebula in the LMC, which suggested that it may have an excess of massive stars and which inspired much of the ongoing discussion of top-heavy IMFs in the distant universe. There have been many other discussions who haven't done specific power laws. I tried putting Alex's numbers in yesterday and couldn't actually find a power law that would reproduce them. So there is a lot of uncertainty, but a lot of people are talking about top-heavy IMFs in the distant universe as being necessary to produce the ionizing flux. But what does that mean? This is my penultimate slide, so don't panic. Well, when people say that the IMF is going from minus 2.35 to minus 2, or minus 2 to minus 1, it's, for a lot of people, it just feels like a number you're changing, and people don't realize how big an impact this is having. In a salpeter like IMF, more than 70% of the stars have a mass below 10 solar masses, and the remainder are in the higher mass regime. By the time you get down to a slope of minus 2, that's these green lines, you've got an almost even distribution of stars. If you're going to minus 1 and you apply that across the mass range, which some people have done in modeling, then you're essentially arguing that less than 2% of all the stars are below 10 solar masses. So you're invoking very different physics, and it's worth thinking about how you would get that stellar population. This is not just a knob you can turn arbitrarily and see what fits without thinking about the implications for the stars themselves. So I would always suggest that if you're using an SP model, and if you're doing any fitting of galaxy populations, you almost certainly are, you should be asking yourself, what stellar evolution models is it using? What stellar atmospheres is it using? What IMF is it using, and in what mass range? What are your compositions and metallicities, and what are your binary parameters and nebula gas assumptions? Now, I've come across as very negative. That is not my intention. We have made enormous progress in the last 20 years or so. We have made progress to the extent that we now have to ask these questions, which before we didn't even have to ask, because we didn't know the level of uncertainty in our inputs. The data is now constraining the models in a serious way, and that's something we are going to have to consider, but also celebrate as a community. I will stop there, and I'm happy to take any questions, although I'm sorry for overrunning.
Thank you very much for that excellent introduction and review, Elizabeth. We do have time for maybe one or two quick questions. I see one over here.
Thank you for a very interesting talk. So my question is relating to galaxy evolution. The co-evolution assumption, at least the way I understand it, is that all the stars are formed at the same time. How do we square away a composite of an entire galaxy spectrum against the knowledge that actually the galaxy will have been a result of a number of galaxy mergers, potentially with galaxies of different ages?
So the majority of galaxy models used for SED fitting are composite stellar populations. So you fit for a star formation history, which says that we've got this much mass of stars with this age and metallicity, this much mass of stars with this age and metallicity. And the relative populations in those different groups is one of the parameters you have to fit for. So if you have a sufficiently complex model, this will accommodate things like sharp bursts associated with merger activity, as well as slow ongoing star formation.
I think we might try and move things along. So Matthew, do you want to get up? And we'll have time to grill Elizabeth in the lunch break. So our next speaker is Matthew Bate, who's going to be telling us about variation of the IMF with redshift and metallicity.
Good. Okay. Thank you to Elizabeth. She's made it much easier to give a 10-minute talk because she's defined so many things. Right. So, yeah. So just carrying on with the IMF theme. As Elizabeth was saying, at least the typical galactic zero-age IMF looks something like this: a salpeter type slope at the high mass end, which is steeper than -2 in a DNDM sense, which means that most of the mass, as Elizabeth was saying, is in the low mass stars, whereas most of the light is coming from the high mass stars. And then we've got some sort of turnover towards low masses, such that at least in our galaxy, the typical star, the most common star, is an M dwarf. And if you go to high masses, they become very rare. And if you go into the brown dwarf regime, there's still quite a few brown dwarfs around, but still fewer than M dwarfs. Okay. And it doesn't really matter where you look. So throughout our galaxy, there's been many different studies over time, and the IMF looks pretty much invariant. Okay, there's not a lot of evidence for strong variations. So the most evidence, I guess, for IMF variations is from the early universe, but it all tends to be indirect evidence. If you go back decades, you've got inferences about them being no metal-free, low-mass stars, for example. That implies that maybe the IMF was produced primarily high-mass stars. You've got the abundances of heavy elements and clusters of galaxies has been used to point for top-heavy type IMFs in the past. You've got the centers of early type galaxies with these high metallicities, high velocity dispersions, and they seem to have very high mass ratios, which you could interpret as being either a top-heavy IMF or actually a bottom-heavy IMF as well. And so there are other models which have proposed, for example, time-dependent IMFs, where you switch from top-heavy to bottom-heavy as the universe evolves and things like that. Of course, this has become even more relevant over the last 2 or 3 years with the James Webb observations of very high redshift galaxies greater than 10. And some of the early papers that came out with these very luminous young galaxies, the quick estimates of the masses of these implied that you might have stellar masses which were greater than the amount of gas in your halo that's produced your galaxy, which of course is completely impossible and implies a star formation efficiency greater than 100%. So some of these extreme results have gone away, but still the point is, in order to understand how much the mass of these galaxies is, you need to make some sort of assumption about the IMF, right? The stellar mass distribution. And so if we've got a varying IMF, then that has all sorts of implications for galaxy masses, for example, and many other things. So my approach to this is I'm not a galaxy formation person at all. I'm sort of out of my depth here. So I study star formation and actually quite small amounts of star formation as well. Okay, so what I'm going to be talking about today is essentially simulations like this one here, which I published back in 2012. There's a 500 solar mass cloud, about a parsec across. There's turbulence injected in the start, and then you let the cloud go. You get gravity creating dense structures, collapse to form stars and brown dwarfs. So each white dot here is a star or brown dwarf. You can see they're forming in clusters and groups, just like you see in our galaxy, and interacting and so on. Okay, and so this 2012 calculation was pretty much the first one that could reproduce the typical stellar population in our galaxy. Okay, again, low mass stars here. I still can't form sort of large numbers of high mass stars and address things like the high mass end slope. But at least in terms of low mass stellar populations, we get an IMF out of these calculations that's similar to a Chabrier or a Krupa type IMF. And we're modeling every star that forms or every star and brown dwarf, so we can look at multiplicity fractions, as Elizabeth was talking about before, and we reproduce this strongly increasing multiplicity fraction with primary mass. From these sorts of calculations, I think there's three main things that you need to get typical stellar populations from these sorts of calculations. You need to form stars in stellar groups. I don't think that the exact structure or turbulence is that important, but as long as you form stars in stellar groups, that means they can interact with each other as they're accreting. So you need stars forming close enough that as they're being assembled, they're also interacting with each other, both dynamically and through radiation. And that gives you an IMF-like mass distribution, like you see here, from a sort of competitive accretion type picture. And it also leads to this, naturally to this increasing multiplicity with primary mass, for example, because when you have multiple systems interacting, they tend to kick out the low mass objects, and the high mass objects tend to hang on to companions. Okay? And so you naturally produce something like this. And then I also think that the radiative interactions between these protostars as you're accreting and producing your stellar population is actually important for getting a relatively invariant mass function. I don't have time to talk about that today, but I think those things are important. So since 2012, I figure, right, okay, we can reproduce sort of what's going on in our galaxy. So we can then use these sorts of calculations to ask, well, where might the IMF and other stellar properties vary? And so one of the things I looked at first was, does the IMF and other stellar properties vary with metallicity? And so you can think about low metallicity gas. Low metallicity gas you'd think should be hotter because there's reduced line cooling, low dust, low extinction, and so on. If you believe that stellar masses have something to do with the gene's mass, then higher temperatures should lead to larger mass stars. But you can make the converse argument. You can say, well, at low metallicities, you've also got reduced opacities. And that means that once gas does start to collapse down, it can actually collapse to higher densities and smaller scales. And you can have fragmentation on smaller scales and more fragmentation before it becomes optically thick. All right. And that means since your gene's mass scales inversely with the square root of density, that should give you lots more star formation and lower mass stars. Okay. And so you've got these two perfectly valid arguments, but they act in the opposite direction. And so early calculations by Andrew Myers and myself showed that there was no strong dependence of the IMF on opacity. But this is something I went back to in 2019. And there's 4 calculations here, all identical initial conditions, except for the metallicity of the gas. Okay, and so these are calculations from 100th of solar metallicity up to super solar metallicities. You can see on the top here, things don't look very different when you're looking at gas densities and so on. And we used the same random seed in the turbulence to try and minimize the differences other than the metallicity. But if you look at temperature down here, so red is like about 40, 50 Kelvin, something like this. Black is sub 10 Kelvin. You can see here that the temperature structure is massively different, okay? As you expect, on large scales, when you have low metallicities, everything tends to be very hot. When you've got very high metallicities, the cooling is really, really strong. You've also got extinction of the interstellar radiation field. So radiation from the rest of the galaxy just can't get in there, and everything is extremely cold. And so you think, well, there's this huge range in temperatures that should lead to a difference in the IMF, right? And it doesn't, right? So these are cumulative IMFs, sorry about this. So number of stars with a mass less than a particular mass. But the point here is the Chabrier parameterization of the IMF in our galaxy is in here. And all of these 4 calculations are also basically on top of each other. They're indistinguishable, okay? And so you've got this hotter gas, you saw it in the previous slide, right? Which should lead to and does lead to higher Jeans masses on large scales. But this seems to be almost exactly counteracted by these low opacities and stronger fragmentation on small scales, at least in current galactic conditions, okay? Now, there is a difference here, and actually Elizabeth mentioned this in her talk, which was fantastic. About the time I was writing this up, these 3 papers came out, 2018, 2019, pointing out that for solar-type stars, the close binary fractions, so spectroscopic binaries, are anti-correlated with metallicity. So stars like the Sun, about 20% of them maybe are in close binaries. But when you go back to very low metallicities, it's something like 50% of these solar-type stars are in spectroscopic binaries. So there's this anti-correlation. So I thought, well, I'm looking at calculations of different metallicities that should be in my simulations, and indeed it is. And in fact, it was actually right back in the one that I did in 2014 as well. I just hadn't noticed, okay? And so, even though the metallicity doesn't affect the IMF, it does affect other stellar properties, such as multiplicity, for example. Okay, and so as I said at the start, the best indirect evidence we have for varying IMF is actually from high redshift, right? So early in the universe. I'm not talking here about primordial star formation, the sort of, Tom Abel, Volker Brom, etc., over the last 25 years or so. I'm still talking about star formation which is dominated by dust. But even if you go back to high redshift, the point is the cosmic microwave background radiation scales as 1 + Z. So instead of 3 degrees at the moment, it's about 16 degrees, say at Z = 5. And 16 degrees is hotter than the present day molecular cloud temperatures. So that should change the Jeans mass, and you'd expect some sort of effect on the IMF. Okay, and so I did a series of calculations, which was published a couple of years ago now, at Z = 5. Okay, so same sort of thing, low metallicity up to solar metallicity. Sorry about the squares here. You guys really should enable people to use Keynote. But anyway, so you can see here that temperatures at low metallicity look similar to the 2019 calculations. The difference here, though, is at high metallicity, there's no black here. Okay, and that's because you've got the 16 Kelvin temperature floor, which is set by the CMB temperature, right? Cosmic microwave background radiation, really, really long wavelength, penetrates right through the cloud and sets the temperature floor here, increases this Jeans mass. And so this leads you then to IMFs that are the same at low metallicity, but at high metallicity, you actually get a bottom light, sorry, Elizabeth, IMF here. So your typical mass, your most common mass is increased, and you've got this deficit here of brown dwarfs and low mass stars compared to the lower metallicity cases, okay? And so I published a paper just at the start of this year, it depends on whether it's AstroPH or MunRes or whatever, but anyway, a few months ago, where I've now extended this up to calculations with redshifts up to Z = 10 and metallicities from 100 solar up to actually 3 times solar. And what you find is that as you increase in redshift and you increase in metallicity, you get increasingly bottom light mass functions. Okay, and so what I've done with these 20 different calculations is map out this parameter space in terms of how the most frequent stellar mass, so globally, I mean, locally it'd be sort of M dwarfs, how that changes with redshift and with metallicity here. And then I've fit empirical functions to this so that nominally you can then take this IMF and put it into your favorite galaxy formation calculations, for example. Okay, and just to show you, this does have an effect on mass to light ratios. So here, for example, if it's Z equals 10-ish, you manage to have star formation going on in solar metallicity gas, then the mass to light ratio that you get is only 40% of the Chabrier value. Okay, and what that means is if you have a galaxy at high redshift, which has a lot of these stars in it, then you're actually overestimating the mass of the galaxy if you assume a Chabrier IMF than if you actually have got one of these bottom light IMFs. Okay, and so I'm going to finish here, but just to point out that Rob Crane, who's in the audience here, and his PhD student, Anna Durant in Liverpool, John Moores, I'm working with them to try and put this analytic, sort of empirical IMF from the star formation simulations now into galaxy formation calculations and see how much difference this makes. And I'll stop there. Thanks.
Do we have any questions for Matthew? We've got one here.
Thanks. Could I just clarify that the last point you were saying that it becomes bottom light, but otherwise there's no change to the high mass slope. Otherwise things are as expected. The difference is the low mass cutoff.
Right. Okay. So unfortunately, at the moment, I'm limited to modeling sort of 500 solar masses of gas. And so as Elizabeth was saying, we don't expect very many massive stars there, right? So I really cannot constrain the high mass slope at all. It might vary, it might not. This is something that I'm working towards with Rob to try and push these sorts of simulations to higher mass when we can actually say something about the high mass slope. So sorry about that. At the moment, I can't say.
So unfortunately, I think we're going to have to keep moving along, but let's thank Matthew again. And our next speaker is Fergus Cullen, who's going to be telling us about evidence for an unusual stellar population in an extremely metal poor galaxy at redshift A.
Yes. Okay. Yes, I'm going to talk about this galaxy that we've observed recently with JWST at high redshift, which is extremely low metallicity and shows some signs which I'll describe of having a non-standard population of very massive stars. So just to quickly describe where this comes from, this is from a Cycle 2 survey called Excels that I'm leading with Adam Carnell up in Edinburgh. So the full survey is lots of galaxies across a wide range of redshifts. But what me and my group at Edinburgh have been working on is these galaxies above redshift 3 in blue here. This is mass versus redshift, focusing on chemical abundance determinations, which we can now do very accurately at these redshifts because of the exquisite depth and sensitivity of JWST. And just before I begin describing the object that is the subject of this talk, I just want to briefly, for those who might be interested, summarize some of the recent papers that we've put out over the last 2 months from this survey. So this is from my student, Thomas Stanton. So there he's been looking at abundances of oxygen, argon, and neon in redshift 4 galaxies. So this is the first time we've been able to do anything like this. We'll have a talk about this later today as well, not from Thomas, but from a different group. Carla, who's going to be talking later in this session, has been looking at carbon, nitrogen, and oxygen at redshift 5. And then my postdoc, Dirk, recently put out a paper looking at strong line metallicity diagnostics using accurate temperature-based metallicities at redshift 3 and above. So if you're interested in any of that, please feel free to ask me about it. But I'm going to focus on this paper, which I put out in January this year, which is looking at this one galaxy at redshift 8.3. So this is it. It happens to be the highest redshift galaxy that we observed in the survey. It wasn't one of the main targets, so it's somewhat serendipitous that it ended up here. But when we reduced the spectrum, it had a large number of interesting properties. So this is what the spectrum looks like. So I'll just go through some of the main kind of intriguing features of this object. So we have a spectrum with medium resolution from JWST NearSpec. It covers rest frame wavelengths about 3,700 to 5,100 angstroms. So we go from the O2 strong line out to O3 5007. If you look at the object, the first interesting thing is that it's very compact. So it's actually unresolved in all of the JWST imaging. And we can use that to put an upper limit on its size of about 200 parsecs. So I'm calling this a galaxy, but it's the size, the physical scale is on something like a giant star cluster in the local universe. If you look at the broadband SED, a notable feature of this is how steep the SED is in the UV. So I'll come back to that later. And then the spectrum, first of all, you can see it has this strong O35007 line, but there's no indication of an O2 line. So this suggests it's a very highly ionized object. And then we have a strong detection of this 4363 aurora line. So for people who don't look at these spectra very often, this might seem innocuous, but this line is exceptionally strong relative to the other lines in the spectrum compared to what's typical in galaxies, even at this redshift. And that's telling us something about the temperature of the gas and the metallicity. So from this spectrum, we have all this suite of lines. We can determine what the oxygen abundance of the gas is, and we can do this accurately because we have this aurora line detection. And when we do this, we find it's actually one of the lowest metallicity galaxies ever observed. So this is mass versus metallicity, and this is the object here. The gas phase oxygen abundance is about 1.5% of the solar value. And this is actually very metal poor, even with respect to other galaxies at the same redshift that we see with JWST. So they tend to be around 10% solar. This object is around 1%. And it's at this kind of flaw in metallicity that we see in dwarf galaxies in the local universe. So these are local universe galaxies in blue, with the caveat that the mass of this object is very uncertain. One difference might be that this is happening in higher mass systems at higher redshift. It's extremely compact. As I mentioned, in all of the JWST imaging bands, you can model it as the PSF. So it's roughly less than 200 parsecs in physical size. And then coming back to this UV slope, so this is the steepness of the UV spectrum on the y-axis. Steeper is towards the bottom. And this is just the UV luminosity. And this is just comparing, maybe you can't see a lot of the points here, but this is just comparing the UV slope that we observed compared to a compilation of literature measurements between redshift 8 and 14. So going out to the highest redshifts that we can see now with JWST. And this again sits at the edge of the distribution. It's one of the bluest objects in the population. So these are all interesting enough things in themselves, but perhaps the most interesting thing is that when you forward model all these line ratios with essentially atomic physics calculations, we use this to derive the element abundances, but we can also use it to derive the temperature of the gas in the galaxy. So I guess you can't see the posterior on here, or at least I can't. But it peaks at a gas phase electron temperature of around 40,000 Kelvin. So this is saying that the temperature of the gas in the H2 region is kind of approximately the same as the surface, I guess, of a typical O star in the local universe. So what I spent the last year doing is trying to figure out if this is physically possible, and yeah, if it is, how would you achieve this? So to do this, basically we used photoionization modeling analysis using a code called Cloudy, which Elizabeth introduced. So I won't go into all the details here. I'm happy to answer questions after if anyone's interested, or you can look at the paper. But the important thing to state is that essentially the most important thing that you need to choose is what's the input stellar ionizing source that you input into Cloudy. And we chose 3 different stellar population models. So one was the BPAS models that Elizabeth has introduced. And these were assuming a standard IMF. So this is a proxy for normal stellar populations that we use to model galaxies at high redshift and in the local universe. And then 2 more extreme scenarios. So one using Wolf-Rayet star models, and one a recent suite of population 3 star models. And these are meant to mimic more extreme stellar populations. You can think of the Wolf-Rayet models, for example, as representing a top-heavy IMF, where you have an excess of, to be specific, greater than 50 solar mass stars. But essentially, the fundamental thing is that these BPAS models allow effective stellar temperatures up to 50,000 Kelvin, but with these more extreme models, you can push that to 100,000 Kelvin or more. So these are the models which we use as input, and we model the H2 region. One of the nice things about this object is it's relatively, in terms of high redshift galaxies, easy to model because we know the physical extent is at maximum 200 parsecs. And I haven't mentioned it, but we also know there's no dust in this object, so we don't have to model the dust attenuation. And we also allow these H2 regions to either be ionization bounded, so a typical Strongen sphere, or density bounded, where you ionize all the gas and some of the excess ionizing photons can escape. And we had this large grid of models that we built and then compared to the observations. So I'm just going to go through the main results of this. So in these figures, each of the panels is one of those 3 input stellar models. And this y-axis is this auroral line to the 5007 forbidden line ratio. And the x-axis is 5007 to H beta. And this top panel is for models with densities less than 10 to the 4 electrons per cubic centimeter. And the color is the temperature of the H2 region that's formed. And the fundamental thing to take away from this is that if you look at normal IMF models, they can't reproduce this high auroral to forbidden line ratio. The more extreme stellar populations can. And if you look at the regions where that occurs, the temperature of the gas is extremely high. So this is saying that these high gas temperatures can be achieved by these more extreme stellar populations. There's a slight caveat in that if you go to very high densities, then you don't need to heat the gas so much. So the standard IMF BPAS models work fine in this scenario. And these densities, although they may be extreme, have been observed in some systems at high redshift. But this is where the steep UV continuum helps us again, because if you plot all our models, and here I'm showing this line ratio, but now as a function of the steepness of the UV slope, to get these very steep UV slope, this steep UV slope that we observe, you need low density. So the color is density here, you need these low density models. And that's because if the density is high, you can form very compact ionization bounded H2 regions. And in that scenario, you would get a strong nebular continuum contribution, similar to what's been seen by Alex and Harley and Ayush have looked at these objects that we can see in JWST, where they have this very flat UV spectrum, the Balmer jump. And this is a nebular continuum dominated galaxy. But the UV slope would be flat, whereas the one that we see from the photometry is very, very steep. So this essentially rules out the bottom row of panels, so we're left with this, which is saying that the best way to explain these observations is with a very hot ISM, for which you need some extremely hot stellar population to power that. So just out of interest, this is the best fitting model. So we have an effective stellar population temperature of around 90,000 Kelvin, which can heat a volume of gas, which has a radius of around 50 parsecs, to around 34,000 Kelvin if the metallicity is around 2% solar. And it's a density bounded region, so a lot of the ionizing photons actually escape. So the escape fraction implied is around 70%. And this H2 region it does a very good job at reproducing the line ratios, the line luminosities, and this steep UV continuum slope here. I'm running out of time, so I'll skip this slide. Just to say that this isn't the only object that looks a bit like this. So there's another object at redshift, basically the same redshift. But this has been lensed. It has a spectrum, but it's not as high resolution. But from the analysis that these authors do, they also infer evidence for very low metallicity in a top-heavy IMF. But what's nice is because it's lensed, you break up the unresolved object that is in our imaging into what it probably looks like, which is this amalgamation of different star-forming clumps. And likely what we're observing is one very recently formed clump that's been triggered by a recent accretion of pristine or near pristine gas. And this object is here. So it's also one of the lowest metallicity objects we know. And I'm out of time, so I'll just leave up my summary slides. Thank you.
Thank you very much, Fergus. We do have time for a question or two, so I'm going to go to...
Thank you for a very interesting talk. I was wondering, perhaps this is a silly question, but would you expect any Wolf-Rayet star features to pop up in your spectrum or not?
Yeah, so we do model this. I think it's one of the things that is slightly confusing still about this object, but I think what's happening is that there is an older stellar population in here if you model the full SED, and the continuum light in the optical is dominated by that older stellar population. So much so that the stellar Wolf-Rayet feature in the optical you wouldn't expect to see when we model the full thing. If we had a UV spectrum, then you should see strong Wolf-Rayet features in the UV, but unfortunately we don't. But we could do with JWST, so hopefully we'll get that in the future.
Got time for another question.
Yeah, thanks for the nice presentation. I was wondering, why do you exclude a priori dense H2 regions with holes rather than just density or radiation bounded? Because that could be also a way to achieve both things.
That's a fair comment. So we did all this modeling, but it's in some sense like the simplest scenario that you could model. And something that, would be good to do, and hopefully maybe in the future I'll have time to, is try and model more complex geometries for the H2 region, just to be more sure about this. Yeah.
So I think we can take one more quickly.
So the observed spectrum includes the region of the nebula, potential nebula 4686 helium-2.
Yeah.
So it's not jumping out from the spectrum you have, but is there any limits you can use the limits on the nebula helium-2 to say more about the population responsible for the nebula?
Yeah. So in the best fitting model, we output the predicted nebula helium-2, which is at about the 2 sigma, like it would be detected at about 2 sigma in the spectrum. And if you look at the exact region, there's maybe a hint of something, but I think it's like just unfortunately in the noise at this point.
Okay, I think let's thank Fergus again. We can move on to our next talk, which is by Guido Roberts-Bassani, who's going to be telling us about the nature and role of luminous galaxies from independent sightlines.
Okay, good morning, everybody. I want to thank the organizers, first of all, for putting on this great special session today, which I'm very excited to be part of. I want to talk about a little bit of work that we've been doing over the last few years in trying to place these sort of exotic luminous objects at high redshift into context of the global galaxy population. So that's sort of the title of my talk. To do this, traditionally up until now, our flagship telescope to study these luminous populations has been the Hubble Space Telescope, helping us map out the evolution of especially bright objects out to a redshift of 10 or so, but this has been, dominated with imaging or photometry. And the arrival of JWST, of course, has extended this redshift frontier now beyond a redshift of 10. It's given us longer wavelength coverage with which to search for especially high redshift galaxies. And crucially, the big development in my eyes has been that we've been able now to take spectra of these galaxies, probing the full rest frame UV and most of the rest frame optical with which to constrain their underlying physics. And so within the first weeks, really, after the arrival of JWST, we set out to look for redshift greater than 10 objects. These are 2 examples up here, which we as part of the GLASS team found at redshifts 10 and 12 or so. Other teams had similar efforts, and if you put all of these together and convert their number densities to star formation rate densities, you get what you see on the left plot over here. So Hubble points are in blue and JWST points are in red. And you can see that there's this general agreement at low redshifts 6 to 10 or so. But beyond a redshift of 10, we find far more luminous galaxies, especially luminous galaxies beyond a redshift of 10, that are in tension with theoretical models and extrapolations from lower redshift. Now, we're in a room full of theorists and observers, and I think this nicely summarizes the state of the field, but in theory, there's no difference between theory and practice. In practice, there is. And so that sort of highlights the fact that we have lots of different theories to try and explain this excess of luminous galaxies. That might be an evolving star formation efficiency. It could be a non-universal IMF, which was being touched on today. Stochastic star formation histories, which temporarily boost the UV luminosities of these galaxies, or even dust clearing from radiation-driven outflows, which remove this sort of dust that blocks the UV light of these galaxies. Now, spectroscopy, of course, is key here. We need to make sure, first of all, that these galaxies at high redshift truly lie at high redshift. And spectroscopy above a redshift of 10 has now become routine with JWST. Here are just a few examples. You can see all of these spectra actually look remarkably different at redshift greater than 10. And we now have somewhere on the order of 25 to 30 confirmed objects above a redshift of 10. Now, if we study the properties of these galaxies from the spectra, we see that some of these are indeed especially luminous. You know, they reach out to redshifts of 14 or so, and they are far more luminous than the general population of galaxies that we see within those redshifts. Studies of their rest frame UV line emission indicate abnormal elemental abundances. In particular, Alex's work, for instance, showing that these objects have enhanced nitrogen relative to their oxygen abundances, possibly tracing second-generation stars. And some of these, of course, also show the Lyman alpha line, which indicates that they've blown out this ionized, large-scale ionized bubble within a heavily neutral medium. So what's going on here? And the question that I tried to bring forward is, are these galaxies representative of the global population at redshift greater than 10, or are they biased in some shape or form? And in particular, are these exceptions to the rule only seen at redshifts greater than 10, or can we learn something at lower redshifts where our samples are a bit more complete and we have larger spectroscopic coverage? So we tried to do this with one instance. These are stacks of near-spec prism data with JWST, trying to derive representative spectroscopic templates with which we can study the stellar populations and gaseous properties of high redshift galaxies and compare them to these redshift greater than 10 monsters, let's say. We can have a look at their ionization fields through the ubiquity of their carbon-3 emission. You can see some of these are consistent with the general population. Others lie above or below it. We can look at the ionization and excitation conditions as a function of their rest frame optical lines. And we see, again, some of these are consistent with the general populations. And we can also look at their UV slopes indicative of the dust content. And again, some of these agree and some of them don't. So what's going on over here? I'd argue that even these stacks are slightly lower luminosity compared to these sort of blue luminous monsters. And so perhaps we are not comparing apples to apples. So this is where I introduced the Borg JWST survey. The objects that we found, there are only a few objects at redshifts greater than 10 in these deep fields that are as luminous as those sort of 2-3 examples. This is highlighted by this plot over here, which showcases the dangers of cosmic variance. That is to say, if you get a cosmological volume, you place your survey area in one part of the universe, you might find an underdensity of luminous objects. If you place it in another part of the universe, you might find an overdensity of those objects. So this is the danger of cosmic variance, and you really have to probe very large areas to find the most luminous objects. This is what we did with the Borg JWST survey, which is shown here in blue as a function of limiting magnitude and the area covered. We use what's called a pure parallel technique. So whilst Hubble was looking at its main fields, in parallel, it was observing randomly across the sky. And so we end up getting a very, very large area over reasonably shallow depths with which we can look for the most luminous populations. And we got JWST time in cycle 1 to follow up some of the most promising luminous candidates. And this is what you see here. This sky map showcases the random pointings that our selections come from. And over here on the right, you can see the low cosmic variance bias as a function of absolute magnitude that our survey probes. None of the JWST surveys to date are able to probe the low values that Borg is able to probe, and we are comparable with the areas probed by Euclid, for instance. So this just highlights a little bit of the power. So we followed up our targets, and the first port of call was to determine whether they really are at high redshift. And we find here in blue, these are all of our confirmations at high redshift. And in red, we have a few examples which turned out to be interlopers. So we confirm a very high number of our selected targets. Here we also have legacy value within this survey where we filled the near spec MSA with lower redshift candidates, and we have, you know, a few tens to 100 or between a redshifts of 1 to 3. And these are the colors of these galaxies and the sort of selection area that we use to select our targets, and this works reasonably well. Now, with these confirmations in mind, we can figure out whether these luminous galaxies are actually, or these abundances are actually real or not. And at redshifts 8 or so, we find they are. These are our red points over here. You can see compared to some JWST points and Hubble points, we lie slightly above them, suggesting that we are uncovering this until now missed population of especially luminous objects, and similarly at redshifts 9 or so. So this sort of alleviates a little bit of the tension that we see in these larger numbers of galaxies at redshifts greater than 10. And I would argue that these galaxies, actually, if we look at their absolute magnitudes as a function of redshift, are perfect analogs with which to study the physics of these luminous greater than 10 objects. You can see that they lie right in the heart of the so-called reionization era. So right in the neutral era, we can probe whether they are able to sort of burn out these ionized bubbles. They are unbiased by definition of their selection, and they are also extremely luminous. These are some of the most luminous galaxies confirmed to date, and crucially, with NIRSpec, we have the full rest frame UV and full rest frame optical coverage with which to unlock their physics, which these redshift greater than 10 sources generally do not have. So you can see here their UV continuum slopes, for instance. This is compared to the luminous redshift greater than 10 objects, which are selected to be particularly blue, so dust poor, generally speaking. One of the hypotheses, again, is that they have cleared out their dust. We find that these objects are analogs to these redshift greater than 10 ones, suggesting they are also dust poor and they're compact. And then finally, we can also look at their rest frame UV emission. This is where a lot of the sort of abnormalities are seen in these redshift greater than 10 ones. I'm plotting two examples here. One of our glass sources, redshifts 12 or so, which we confirmed with NIRSpec, which show you these very, very strong carbon-4, oxygen-3, nitrogen-3, and carbon-3 lines, suggestive of really harsh ionization fields, and also these enhanced nitrogen abundances relative to oxygen. And another one, GNZ11 in purple, which seems to be a little bit more normal in this regard, not showing these crazy lines such as this glass object. And if we stack these analogs, these luminous analogs at slightly lower redshift to determine whether the populations show similar line emission, you can see that it's a little bit different. Here in black is that stack. Carbon-3 is prevalent, as we saw in the general populations, but the rest of the lines don't seem to pop out as much as these exceptional objects. But crucially, again, we have the rest frame optical with which we can try and determine whether there is evidence of supermassive black holes. We don't see any strong evidence of supermassive black holes, but this, of course, is key to disentangle star formation from black hole activity, such as in these two objects here at redshifts greater than 10, where MIRI spectrum has been taken, but MIRI is pretty prohibitive to look at redshift greater than 10 sources. Lastly, we can look at whether these representative luminous objects at redshift 7 to 9 have carved out early ionized bubbles in a neutral medium. These are two galaxies which we find are merging close together, and in their NIRSpec prism spectra, we see Lyman alpha in both of them. We don't see any Lyman alpha in any of these other objects, suggesting that in general, the intergalactic medium is neutral, and these sort of remarkably luminous objects are not able to carve out an ionized bubble on their own. It really depends a little bit on environment, and so we can compare to stacks of Lyman alpha emitters and stacks of non-Lyman alpha emitters to see whether their properties look similar. So this is an example that I had done with a stack of Lyman alpha emitters at redshifts greater than 5 and stacks of non-Lyman alpha emitters where you can see a very clear difference. The Lyman alpha emitters have very strong rest frame UV lines, are very dust poor, and they have this so-called Balmer jump over here, suggestive of very young stellar populations, very harsh radiation fields, and possibly some AGN signatures as well. So I think I'm out of time. I'll leave it here. These are my conclusions, that the spectroscopic confirmations of studies of redshift greater than 10 objects have now become routine with JWST. However, they lack the rest frame optical with which we need to infer whether these objects have AGN present within their spectra. So what can we learn from lower redshift? Borg can answer this because it offers a representative sample of high redshift luminous objects that now have full rest frame UV to rest frame optical coverage. Within these spectra, we don't see crazy UV line emission, as in some of these redshift greater than 10 objects. Lyman alpha emission is scarce as well, and we don't see any major AGN activity. And so this survey really highlights what you can do combining the power of HST pure parallel selections with JWST follow-up. So thank you very much.
Questions for Guido?
The question remains why the volume density of the monsters greater than a redshift of 10 is so much higher than from 7 to 9. What is that ratio? It must be very big.
Sorry, can you say that again?
The volume density.
Yeah.
You know, in a small area that's been scanned beyond a redshift of 10, we found these monsters. Within this big area in Borg, you found a few.
Yeah.
But the volume density between those two samples of the monsters must be much higher at redshift greater than 10, I would have thought, isn't it? And so the question remains, why are they so common beyond a redshift of 10?
It's unclear. I don't know. We haven't done a direct comparison, but clearly I think cosmic variance plays some role. I mean, these redshift greater than 10 sources are generally found in 1 or 2 fields as well. It's not like we find them in every single field. So I think cosmic variance plays some role in that. And, you know, for instance, in the goods fields, we find this excess of redshift greater than 10 objects. But then if we look in some of the Canucks lensing clusters, the density of objects drops precipitously and follows in apparent accordance with what we'd seen with Hubble. So that's a nice illustration of the dangers of cosmic variance. And hopefully, you know, Euclid, for instance, will be able to answer this a bit more, follow-up of Euclid sources.
I think we've got time for one more question.
Could you expand a little bit on your AGN determination? So why can't you say that it's an AGN or not with the UV spectrum? And what is the unique signature that you get in the optical spectrum?
Okay, so let me break that down a little bit. So we can't say anything definitive just yet with this spectra. The reason for that is that they are too low resolution and too shallow. So in the rest frame optical, it's difficult now to use a BPT diagram because we're going down to lower metallicities and higher radiation fields, and so these two populations start overlapping. We can look for broad line signatures in their Balmer lines, for instance, and this is where you need higher resolution, but at first glance, we don't see anything crazy, let's say, within these prism spectra. So that's the rest frame optical. And, you know, in other objects, we have seen broad line features in these similar prism spectra. So they are able to probe them. In the rest frame UV, it's very difficult as well because the prism's resolution is at its lowest. So you often blend out these rest frame UV lines. But if you take the ratios of the ones that you do see, you see that generally speaking, these objects fall right at the intersect between the AGN and the star forming sources. Now, one thing that would be interesting, which is usually much more of a telltale sign, is if you can find nitrogen-5 emission in the rest frame UV, which requires something on the order of 78 electron volts to excite. And that's very difficult to do with metal poor star formation. You really start edging towards AGN. So if we can look for that signature, that would reveal a lot. But again, you need higher resolution spectroscopy, and we're trying to get that data. So we can't say anything conclusive yet, but I think we can rule out crazy AGN.
Okay, let's thank Guido once again. And our next talk is going to be from Sophia Fleury, talking about bringing together theory and observation with modeling tools.
Hello, everyone. As Effer mentioned, I'm Sophia Fleury. I'm currently a postdoc at the University of Edinburgh, and I'm going to talk to you today about developing and utilizing some of the tools that we have at our disposal, or proposing new tools that are going to be at our disposal to try to understand what we see in the spectra we observe. So first and foremost, you've heard a little bit about this today already. How do we interpret what we see in a spectrum? So you saw from Fergus, building lots of cloudy models. You can use facilities like PyNeb to try to measure metallicities. You can use throwing lots of Gaussians at your emission lines to try to get your kinematics out, and maybe doing some work with some semi-analytic line profiles. But this is sort of generally what people like to do with their emission lines, some of their absorption lines. And when it comes to stellar populations, people generally like to use stellar models like CMFGen, power. Sometimes they will do more sophisticated approaches to modeling, like the SEI method from the 1980s, or more sophisticated Monte Carlo integrations to try to predict your P Cygni lines and your stellar populations. You can see here an example from a recent work with low metallicity massive stars in Leo P, where you can try to reproduce the observed spectroscopic features, the P Cygni lines in spectra, by using sophisticated stellar population models. So you can see here, sort of different, by varying the mass loss rates, you can get different looking P Cygni features that are either very broad and have very prominent emission and absorption features, or not, depending on what your input physics is. First and foremost, I'm going to address the need for some new ionization models. So to date, people have been using sort of outdated abundance patterns. They have not been uniformly applying the latest and greatest atomic physics. They haven't been using dust physics the way they ought to. They haven't been accounting for the density profile or the gas geometry appropriately in order to robustly explore parameter space to try to calibrate their diagnostics and to understand galaxies both locally and at high redshift. And one of the important things that people have not considered that they really need to or ought to are astrophysical shocks, which can be a really important component, especially in the case of massive stars, where you either have stellar winds that are blowing bubbles and creating shock waves in the interstellar medium, or in the case of supernovae, where a star explodes and you get a blast wave. And we see evidence even for very young stellar populations and massive star clusters locally, like Markarian 71, where we see these nice broad, like nitrogen-5 lines and carbon-4 and helium-2, and evidence, again, also for some very dense gas conditions that may be suggestive of some shock excitation. And to account for, say, the dense gas that we see both locally and at high redshift, shocks can provide the compression of gas that we would think of as being at more characteristic densities through super adiabatic or approaching isothermal cooling or density structure. We can progress from, say, a factor of 3 gas compression up to several orders of magnitude. And so if we're starting at, say, 10 to the 3, 10 to the 4 parts per cubic centimeter, we can very easily enter that high density gas regime that we seem to observe at high rate. And so shocks can account for some of these very extreme conditions that we think we see. And so just to give you a sense of what we can do by varying, as we heard earlier today, the input spectra, you can account for stellar binaries. In your input spectrum, you can use single star as stellar population templates. You can vary your AGN input spectrum depending on the Eddington rate, the black hole mass, and you can also get an ionizing spectrum from a shock. So the shock, as it cools in the very high temperature regime, can emit a Bremsstrahlung spectrum that will actually ionize precursory gas before the shock front arrives. And so you can see in this case of a 500 kilometer per second velocity shock, you actually get an emergent spectrum that can ionize gas very much like an AGN could. And so this can affect our diagnostic parameter spaces. And so I did this for the latest and greatest set of atomic data and empirical abundance patterns calibrated on OMB stars. And I've compared that to observations of local and distant galaxies. So over here is a diagnostic for some of our brighter lines, like you saw in the spectrum in the talk before. We could try to, say, put those bright emission lines on this kind of diagnostic to try to distinguish between, say, AGN excitation, star-forming galaxies. And you can see that they actually very nicely separate between those photoionization sources due to the fact that the ionizing SEDs are different at these, say, the carbon-4 and helium-2 ionization thresholds. And so you get this nice demarcation that happens in the models. Shocks, on the other hand, can be a little tricky, as you could probably guess from what you saw from the ionizing SED from the shock. You do get some overlap with AGN, but shocks can occupy a very niche space in between the AGN and star-forming galaxies, where you can sort of, in this middle part here, you can occupy this unique space where you have low velocity shocks that aren't producing the ionizing spectrum, but are still heating the gas and making the gas more dense. And so that can actually account for a lot of local star-forming galaxies that have some weird high ionization lines, but also galaxies at high redshift that exhibit a nitrogen excess, which is really interesting because those galaxies have been attributed to, say, AGN and very unique star formation histories and some weird enrichment scenarios. But if we start to account for shocks, this might be able to explain our observations. And so over here on the right, I'm showing what happens if we look at specifically the nitrogen-3 quintuplet, which is extremely density sensitive. And so when you start to look at shocks, these can start to explain the observations that we see at high redshift. And so you can see that for the most part, the shock models, as you get to lower velocities, and so you move away from the AGN regime where you're dominated by the shock photoionization, and you're looking at the post-shock gas dominating the emergent spectrum, you can start to recover the observed flux ratios in a lot of these high redshift galaxies that otherwise we haven't really been able to explain. And this assumes standard abundance patterns that we observe at low redshift and gas densities that we also observe at low redshift as the input to the shock models. And so we're talking 10 to the 3 parts per cubic centimeter and roughly like 30 to 50% solar metallicities. And this can almost completely recover these. And if you account for, say, the scatter, the dispersion that we see in nitrogen abundances at low redshift, that can actually fully account for these. Now, everybody's favorite wonky galaxy at high redshift is still an outlier. GNZ11 is this weird thing all the way up here. And so that's still very comfortably weird. And so we can still get excited about that. But for the most part, these galaxies here, both some of the weird lower redshift galaxies that exhibit nitrogen excess, like Markarian 996, and the sunburst arc at its cosmic noon, also fall in this regime. And so by properly accounting for all these effects within our suites of ionization models, we can start to get a more holistic, more astrophysically complete sense of what's going on in galaxies. And because this is the low velocity regime of shocks, this is something that we could probably comfortably attribute to massive stars driving hundreds of kilometers per second winds. I got ahead of myself. In addition to that, we need to understand our line fluxes, but we also need to understand the velocity shapes, the velocity profiles of the emission lines themselves. And so to date, most of what people do is they empirically measure the quantiles, like their full width at half maximum of their emission and absorption lines, or they just throw as many Gaussians as they can at their line profiles until they get a small enough chi-squared that they say, okay, we've set aside some Bayesian information criterion, we're done, we fit all of our Gaussians, we're happy. But this lacks a lot of physical motivation because you're saying, okay, there's some wind driving a thing, and then we're going to model it using a random velocity field. And that doesn't really make sense. That doesn't seem to be physically or rationally consistent with how we're interpreting what we see. And so I've decided to devote some time to trying to rectify this with some software that's going to be publicly available on GitHub and through pip install in the near future. So this assumes some sort of velocity field that's related to the wind physics. So you have your various choices of how you think the wind is being accelerated. You have some choices about how the gas is distributed across your wind. So you can either get these pulse-like things where you have, imagine an expanding shell, and that's being driven, like, say, in a single blast wave or a single pulse-like episode from a star. Or you can have something that's more continuous, which observations of nearby Wolf-Rayet stars suggests is what's the case when you have multiple pulses, and those pulses dissipate on timescales much smaller than that of the outflow. You can actually form an exponential or power law-like density distribution. And that's what we start to see in say, AGN and starburst galaxies. And so when we assume some sort of geometry, whether it's some sort of bicone or some sort of a sphere, we can integrate over that velocity and density field to start to produce line profiles that are unique in their shape and can actually tell us something about the underlying physics of these winds and galaxies. And that will tell us something about how to interpret what we're observing, say, from stellar populations. And so this is a nearby H2 region. I'm looking at H beta, where you can see that there's these broad underlying wings, and you can run some MCMC algorithm with these sophisticated spectral lines to tease out something about what's actually going on with the underlying wind. And so in this particular case, This is a 4 million year old stellar population. We don't think supernovae are at play, and so there's got to be some sort of line driving. And this tells us from what we get out of the sophisticated line profile modeling that we're seeing that there's gas that's able to escape its ionization or its gravitational potential. We've got a velocity field that's consistent with line driving through sort of optically thick winds. And we've got a density profile that indicates that there's sustained successive pulses of wind. We can do something similar with P Cygni winds. So I'm doing this here with the N5 line from young stellar populations and a stack of UV spectra of Lyman continuum leakers in the nearby universe. And this is indicating that these stars are producing winds in the order within the vicinity of the stars, say about 3,000 kilometers per second in their terminal velocity. And so this can tell us something about the relative importance of the feedback from these stars in shaping the geometry of the ISM. So to conclude, there are a lot of things that we can do to try to improve the way that we're interpreting the spectra that we observe of galaxies and H2 regions in both the local and high redshift universes. I've presented some new ionization models that can allow us to properly or better interpret the flux ratios that we observe in galaxies that probably host Wolf-Rayet populations. And there are also ways to improve our interpretation of weird, broad, asymmetric line profiles, both in absorption and in emission, to try to improve our assessment and understanding of the effects that these massive stars can have on their environments.
Questions for Sophia?
Thanks. Very nice talk. Interesting. A question about the shocks. When we tested these possibilities with Stéphane Charlot's group, what we found was that shocks are in general very good when you consider line ratios and diagnostics diagrams like this. But when you start considering the luminosities emitted in shocks, then it becomes very hard to justify from the energy in shocks to produce enough flux, enough luminosity to dominate those lines with respect to star formation. So I don't know if you've looked into this.
I have looked into this. This is something I've been working on with a graduate student, and there's a forthcoming paper looking at composite ratios of say AGN in shocks or AGN in star formation or star formation in shocks, and what happens when you try to combine these things, accounting for the predicted luminosity of each model. And you're right, that can be problematic. Sometimes shocks are sort of swamped by the stellar population. So yes, that is an important caveat.
Do we have any other questions? If not, we can move to the next set of talks. So let's thank Sophia again. So next up, we're going to change pace. We're going to have a string of 3 flash talks. So can I ask Sophie and Suradeep also to maybe just come and sit in the front row for the next couple of talks, and we'll start with our first flash talk, which is by Ankur Upadhyaya, talking about the effect of stellar IMF variations on nebular emission lines in both normal and compact sources.
Thank you, Alex. So I'm Ankur Upadhyaya. I'm a PhD student at the University of Warwick, working with Elizabeth. And today I'm going to talk about the effect of stellar IMF variations on nebular emission lines in both compact and normal sources. So the motivation for this study comes basically, so many of the speakers have already made the case for IMF variations. So it's just one of our project is also just one of them. So people have invoked stellar IMF variations to explain the excess of UV bright galaxies at very high redshift. And also the abundance of very massive stars has also been invoked to explain the nitrogen enhanced sources suggestive of a top heavy IMF. Also, top heavy IMF has also been invoked to explain sources with rather nebula dominated galaxies like Alex and I's paper. So basically we want to explore more about this, how stellar IMF variations affect the nebula emission lines in galaxies. And we also want to recalibrate the BPT diagrams for top heavy IMFs and also for sources with high electron density. So we feed different BFAST version 2.2 ACDs for different IMF variants to the photoionization cloudy with various radius and electron density parameters. We run hundreds of thousands of cloudy models at different ages. And so the methodology that we obtain that, so here is, so like it's an IMF plot with, so basically this is higher end slope of the IMF. And we have models, the ACDs goes from with slope of -1 to, in our case, in this project, -2.4, the standard saltpeter value being like -2.35. And we feed these ACDs to the cloudy models. And we have two sets of combination. So this is like normal combination with radius from 5 parsec to 10 parsec and electron density from 100 to 1000 centimeter cube. And for these compact combinations, which take radius 0.5 parsec to 10 parsec, and then very high electron density from 10⁴ to 10⁶ centimeter cube. So this is just preliminary results that we got. So this we have looked at so many different lines. So more interesting lines would be like the helium-2 1640 Armstrong, the UV one. So here you can see like this is for each of the plots on like vertical axis, you have the helium-2 flux, and this is A's. So it is evolution of helium flux with A's, and sources with more compact radius are on the top, and sources with higher electron density on like on the right hand side, the plots with higher electron density. So there are some of the cloudy runs that have failed in extreme systems. That is for 0.5 parsec and 10⁶ centimeter cube. So some of the runs fails at these extreme conditions. But overall, the thing that you see here, like there's a peak of helium-2 flux at 2.5 million years. So that is basically massive stars or very massive stars contributing at this age, like because the very massive stars die down after 2.5 million years. So, and you got like very high ionizing photon at 2.5 million years from massive stars or very massive stars. So this is for like 5% of solar metallicity. And we have looked at like 10% solar metallicity. The trend continues. You can basically see same kind of stuff. The flux peaks at 2.5 million years. But if you move down and see like at 50% solar, so half of solar metallicity, you see that the flux at 2.5 million years like decreases very, not as strong as like it was initially. So it basically it's not, it decreases. And the reason for that is because, you know, at this metallicity, the stellar winds are very, very strong. So the helium from the surface of the stars get it comes to the stellar atmosphere, and the helium-2 flux from the stars itself, like the flux to ionize the helium gets absorbed within the stellar atmosphere, so it won't escape to the nebulae of the sources, so it won't ionize the nebula helium-2, or like or the effect won't be strong. So because of the absorption of the helium ionizing flux within the stellar atmosphere at higher metallicities. So that is the helium-2 flux. And we also looked at the BPT, some of the BPT diagrams. We have just looked at like N2 over H alpha, and this on x-axis you have N2 over H alpha, and on y-axis you have O3 over H beta. So there is some change on like this extreme system, this is 0.5 radius of 0.5 and 10⁴ centimeter per cube electron density. But overall at other, if you look at other cases, and you have like, these are the different colors are like for different IMF variants. So we don't see much change with the IMF, but maybe we are looking at to be honest, we are probably looking at different like wrong BPT plots. It's pointed by Fergus. Like we might have to opt to look at other different plots. So yeah, we don't see much change with the with the different conditions with different parameters. So yeah, this is for different values of metallicity, and so basically we said that like there's no significant change and no variance of, so BPT diagrams are probably safe for now. So thanks. And we are like next. This is our future work, and if you have any feedback, if you want to look at other lines for, then you can contact us. Thank you.
Okay, let's thank Ankur. So I forgot to mention the flash talks, we don't have time for questions, but you can ask questions at the lunch break, of course. So our next flash talk is going to be from Sophie Newman talking about cloudy Mariston.
So yeah, hi. Yeah, as said, I'm Sophie. I'm a second year PhD student at the University of Portsmouth, being supervised by Claudia Mariston and Christopher Lovell. And my job is to very, very quickly convince you that stellar rotation and Wolf-Rayet stars are very important. So as we know, in the high redshift universe, we've been seeing lots of emission lines, very strong emission lines. And so that makes us wonder, what is causing these? What are driving these very high ionization? And so one thing we could look at is stellar rotation. So these lead to hard ionizing spectra. We've got more flux at those smaller wavelengths, and you get greater luminosities. And this is basically because you've got lots of rotational mixing, higher temperatures, more photons that can ionize different lines. We also have these Wolf-Rayet stars that are very pretty. These have very, very strong winds and lots of ionizing photons as well. It's very, very short phase, but as Elizabeth said earlier, you only need a few of these stars to kind of make quite a big impact on your total spectra. And different models will look at these in different ways. And basically what most models do, they use these corrected effective temperatures because of the large extent of the winds. And I'm going to show you what happens if you don't do that. So I'm going to very quickly go over some stuff that came out in my paper that I submitted in January. And we looked at these new Marston 24 models. These basically use the new Geneva tracks that include rotation. And we see the impact of that. And they also show the difference between the corrected temperatures and the non-corrective temperatures for Wolf-Rayet stars. We also look at a variety of other models from BPAS to BCO3, Starbus 99, FSPS, and these all have very different input physics that have been assumed. For example, MIST also, the FSPS uses MIST as their input tracks, and that also uses rotation, but in a different way. You've got our binary stars, you've got whether things use non-thermal equilibrium, that kind of thing. As well as different libraries, whether those libraries include Wolf-Rayet stars, whether it's theoretical, empirical, lots of different assumptions. We use the same modeling for all the different models, and we use cloudy with different ranges of parameters that have been varied, and we get this. So these are different predictions for different line luminosities, and for the lower ionization lines like hydrogen here, they grow pretty well. But for your higher ionization lines like O3, there's a larger difference. So for example, the red lines are the Marston models, and the dashed line is without rotation, red is with rotation. And you can really see how much it boosts those line luminosities. You can see models like BPAS, they have much higher luminosities for a longer amount of time. And you can see these peaks around 3 megayear, where you got the Wolf-Rayet phase starting to come in. You can also see this when you look at the ionizing photon production rate for O3. And yeah, you've got these huge differences, which really show it's really important to think about which models you're using, what physics they're considering. And this is showing the different variations for the new Marston models. So you have your models rotating, non-rotating, as well as your models with the corrected Wolf-Rayet phases and non-corrected Wolf-Rayet phases. And you can see that the models that lead to the most photons being produced that can ionize O3 are the rotating models without the corrected temperatures. Now, the corrected temperatures might be needed for a realistic population, but you can see here the impact of those different assumptions. Why is this important? So if you're coupling this with your cosmological simulations to do forward modeling, you're going to get very different outputs. But also if you're doing SED fitting, you're going to get different predicted parameters for the data you're looking at. Yeah, I've probably gone too quickly, stressing, but yeah, you can find the models online, and there's lots of like nice notebooks to help you look at those.
Thanks very much, Sophie, for a very, very well-timed talk. You brought us back another minute. So our next talk is going to be from Suradip Bhattacharya, talking about probing cosmic chemical enrichment.
Yeah, hi, I'm Suradip. I'm a Carr Fellow at the University of Hertfordshire. And I'm basically going to be talking about probing chemical enrichment in star-forming galaxies with oxygen and argon, which are two of the elements. So normally this plot is from Chiaki, which basically shows that a bunch of different elements, the periodic table, have contributions from origins from various different places, which can be either from supernovae, core collapse type 1a, AGBs, Big Bang nucleosynthesis, and so on. If you look at oxygen and argon abundances, you can look at oxygen, which comes mainly from core collapse supernovae, and argon, which has both core collapse and type 1a supernovae contribution. This sort of stuff has been probed for a very long time with different elements in the Milky Way from individual stars by looking at absorption line spectra. We are looking at emission line spectra, and I'm talking about oxygen and argon because you can probe supernovae chemical enrichment from any emission nebulae by looking at oxygen and argon abundances, which have these different lines. The ones in red are the argon lines, and the 4363 line, which is the temperature sensitive line, allowing you to actually measure the abundances. Most of the stuff that I'm going to talk about comes from my understanding by looking at planetary nebulae. If you want your ears to bleed, please come and talk to me later, and I will talk to you about planetary nebulae. Now I'm going to talk to you about star-forming galaxies. So this idea of chemical enrichment has been mostly limited by looking at Milky Way individual stars. Individual stars in the Milky Way, different alpha elements have different abundances, and then depending whether it's on the bulge or in the solar neighborhood, this is from models by Chiaki. But what you see is that depending on the star formation history, the alpha to iron versus iron, a Tinsley diagram, which was made from 13 stars, today I learned, is traversed differently. So if it's a Milky Way bulge, if the star formation history is very rapid, very early on, this diagram is traversed very quickly because type 1a supernovae start dominating the enrichment. They produce more iron. They also start producing more argon. That's why the turnover is seen in both. So you see this differently. If it's solar neighborhood and the star formation rate is slower at early times, then it takes a long time for the type 1a supernovae to start dominating. But you see the effect in both, whether you look at alpha to iron or you look at oxygen to argon. If you're looking at a star-forming galaxy, you're only going to see the latest, newest generation of stars. You're only going to see oxygen to argon versus argon, telling you the state of chemical enrichment in that individual galaxy. If you have a bunch of them, then you should be able to trace out what you see for within the Milky Way, and you can do the same thing at higher redshifts or for any group of any ensemble of star-forming galaxies. So if you take SDSS spectra, which is of course 20-year-old, I know, but no one's plotted this before because I was too busy playing Pokemon in 2005. So it's oxygen to argon versus argon. If you plot this out, you can see that this is the M31 line, which is in red. This is the Milky Way in black. You have relatively more massive. These are M33 LMC mass galaxies, and you have lower mass ones. So for lower mass galaxies, the supernovae turn on relatively more quickly because they're more rapid star formation, and they take some time to basically type 1a supernovae start dominating at earlier times before the core collapse could make the abundances reach higher. So you have the turnover earlier. So there's a mass-dependent chemical enrichment. Now, this is the first time you see it for an ensemble of galaxies. You can also do the same thing at higher redshift because JWST, as you've already seen from previous talks, allows you to make these kinds of measurements. These are from ours, which are 10 archival measurements. This is the paper's already on archive. If you take the JWST points, you plot this out oxygen to argon, you basically can see that some of them lie on the Milky Way-like enrichment, which is good news, which is nice to see after all the negativity. This is actually good news. Your theoretical chemical enrichment ideas are okay up to redshift 3 or 4, but you start getting a few outliers. We are biased to seeing these outliers because if we see the argon line being strong in a survey, it's basically, we are preferentially observing the objects which do have some strong argon line. If we can get the kind of survey for JWST that we see for high redshift, that we see at lower redshift like SDSS, then we should see more objects here. But if these kind of things, you would need to explain them with bursty star formation, which you do expect at high redshift. But there is at least one object which is a conundrum because you would need some sort of additional chemical enrichment source. Here's a pizza.
Thank you very much, Suradip. So our next speaker is going to be Carla Ariana Cordova, talking about exploring the N/O OH relation across cosmic time with Class E and XLs.
Hi everyone. So yeah, I'm Carla Arellano Cordova, and I am a postdoc at University of Edinburgh, and I am working in the research group of Dr. Fergus Cullen. So this is some of my collaborators, and I will speak about Classy, a survey in the local universe, and XLs, that is in the High Redshift. Okay, so I will speak about the nitrogen overall versus OH relations. I think these days are very famous, very, yes, it's like a fashion now. So I here two different plots before all this JWST era. Then you can see here two different components. I focus now in nitrogen, but also taking into account also the carbon can follow a similar things. So we see that in low metallicity regime, we have this plateau that is basically from the massive stars, the primary enrichment that have suffered these stars. But then at high metallicity, we have this secondary component, basically traced for a very low intermediate mass star in nitrogen. Similar thing with carbon. But these two plots here is only with the stars, and you can see the very nice correlation with very low dispersion. However, when we pass to X2 regions, galaxies, galactic S2 regions, you can see all these massive points there, and this kind of correlation get lost. So what is this happening here? What is the cause of this dispersion? When since the 90s or before the 90s, people have been thinking about that, saying, okay, maybe it's the INF. There is also the different sources of how this enrichment is happening. So, but now, in the JWST era, we have also these very high nitrogen enrichments, and we are looking for a scenario to try to explain this very nitrogen overall. So what we know so far is like we have a very high density of environments. Now with JWST, also in the local universe with the HST, we are open to different density diagnostics that can give us information about how is the density structure. But also the JWST opens a new ways to calculate the nitrogen abundances. Before with the optical, we had only this nitrogen 2 diagnostic emission line, but now we have nitrogen 3 and nitrogen 4. And in the local universe here, this is a point for Daniel Berg, that she using HST, we can have nitrogen 3, but there are very few samples that we can study nitrogen 3 so far. So but there is a new data. For example, here is a picture of Corti with a high redshift galaxy of 9 that you can see also this different enrichment that is traced for different INFs. Oh, it's very messy here. Okay, so but to have a complete picture about the nitrogen overall, we need two samples. Samples of galaxy in the local universe, but also in the high redshift, con very well constrained the physical conditions. For example, density, temperature, that can give us the keys to derive robust chemical abundances. So this is Classy. This is a treasury service led by Daniel Berg that is compiled 45 star-forming galaxies with UV and optical observations covering a broad galaxy properties in stellar matter, star formation rate, and ionization parameters. Here you can see the metallicity rate and the stellar mass. So one of the things for the classic galaxies is a very representative of high redshift galaxies. And another hand, we have early the XLs. So Fergus did a very nice introduction about the surveys, and we are in my work I focus more in star-forming galaxies that cover this range of redshifts. So I will start first with Classy in combination with Excel to try to get a result for the nitrogen overall. So this is our result for Classy. When you can see here the background, some of the star-forming galaxies, X2 region, also galactic X2 regions, and in the circle you can see Classy. So one thing that you can see first is that there is a lot of dispersion there. We cover also this broad metallicity, but also there is very high nitrogen enrichment for some of the classic galaxies. Then when we compare with the Excel galaxies, you can see that galaxies that are to redshift 2 and 6 also are in agreement with the classic galaxies, but above the average of the other local systems. So one of the things to explore here with classic is the things that we can have all these different properties from the UV and the optical. We can explore what is driving all this dispersion, specifically to compare with the stellar mass, star formation rate, specific star formation rate. So here in the next slide, well, sorry, and then we have also this separation that is with the galaxy that we have with nitrogen. Here are these distinctions. These galaxies that are high redshift, there are where the nitrogen overall is determining only with UV lines, while the excess galaxies are determining with oxygen, with optical lines. So if we see here, people trying to understand what is really happening. I don't know what happened with my figures. Try to understand what is happening with this dispersion, like the INF in this nice paper from Vicencio 2016. You can see how the variations of the INF can also reproduce this dispersion. So, but one of the results for class in combination with Excel is that you can see here the star formation rate and the nitrogen overall, and you see here the low star formation rate show this plateau with the other, that is also in agreement with other sources of the literature, but then a high star formation rate, there is a correlation with the nitrogen overall. High nitrogen overall means high star formation rate, but also the galaxies are high redshift, align very well with the local star forming galaxies. With the stellar mass, we have more dispersion. It's hard to say here, but with classic and Excel, you can see that there is a good an agreement. And while the galaxies with a high redshift, there is a dispersion there. Here also we compare with two different relationships using electron-like methods. Here, we all use temperature relationships. So you can see here that there is a bit of discrepancy. But in general, for low masses, we have this stable plateau. I don't have time here to say too much about now this topic, but if you are, I'm happy to discuss about what other physical galaxy properties that I compare with classic and high redshift galaxies. But now to understand also how is these sources of the region for nitrogen overall, we also need these individual galaxies that have a different properties. So in this case, I'm using a Excel survey when we have two high redshift galaxies, redshift 5, that we can have simultaneously carbon and nitrogen in the optical, and we can try to understand the evolution of these two elements. So the objective of this paper basically is investigate this carbon and nitrogen enrichment, also the comparison with different other high galaxies. So here is an example of this spectrum. You can see here the nitrogen, the carbon 3 lines, also the oxygen 3 auroral lines that we can give us this temperature and other emission lines. So this is the result. One of the first things that we found with this is the metallicity. We find a very high metallicity in comparison with all these high redshift galaxies that basically are in this part of the relationship. But we find the carbon overall is basically similar to other sources that high redshift, and also with the galaxies in the local universe. We have classic here in also the background, but only you can see that we also have nitrogen enrichment for these high redshift galaxies. So, and we compare now with the other typical plugs, like the carbon and nitrogen. We can see, well, isotope 2023 compared with these dwarf galaxies, and with Lamin continuum emitters is saying that Lamin continuum emitters have this nitrogen enhancement in comparison with carbon. So we did a similar plot here. You can see here in this point, we had the classic survey plus other dwarf galaxies, and then we had the Lamin continuum emitters when measurements these two abundances, and we have here our excess galaxies. So the first thing we can see is that there is like a trend in the sense that dwarf galaxies are separated from the Lamin continuum emitters, and also excess galaxies have a higher, lower carbon and nitrogen. So the high redshift galaxies are occupy this space, and all these high redshift galaxies are explaining for this top heavy INF. So, but to understand more this plot and see what is going on with these galaxies, so we do chemical evolution models to see what is causing this carbon and nitrogen. So one of the things that I want to mention here is the metallicity of these regions. So particularly these are high metallicity in comparison with the other high redshift galaxies that have nitrogen estimates with using UV lines. And with vary the INF of these chemical evolution models, our result is that these chemical evolution patterns for these galaxies are better constrained for bottom heavy INF because the metallicity and because we have these enrichments for intermediate mass star. So this is a exploration about the chemical evolution with these high redshift galaxies. However, we need more samples of galaxies that can give us these two elements to try to understand better this behavior. But also you can see here that the errors in our data is high, and this is due to not only the observational things, also the different methodology that we use. This means that to calculate carbon and nitrogen, we need ionization correction factors that are really very important to trace the gas of these elements. So these are my conclusions, and thank you.
Very much, Carla. We've got time for questions. So I can start with one, which is, so you showed on the previous slide, the variations of IMF in the modeling. Do you play around with so you've got variations in the slopes there. Do you also consider changes in the upper mass cutoff, like how high a mass star you go to in the?
Well, these models were provided for Jackie, and she was playing with all these the things. But I think the most is, like I would say, the more important here it was the metallicity, because she tried to reproduce with similar way that are producing with the high redshift results with the top heavy, and we realized that without metallicity we needed an extra source that can ionize the nitrogen. Yeah.
I was wondering, you plotted the nitrogen abundance over the star formation rate and the mass of the galaxy.
Yeah.
I was wondering if you looked at the nitrogen abundance over the specific star formation rate. Would that reduce or enhance the scatter?
I did it. I did the product here, but we don't find any relation. There is a lot of scatters. Excels and Class C are in the same position, but the green points here are separated. So we cannot see nothing around with a specific star formation.
So did I get it right? It's more scatter
The specific star formation.
with the specific star formation rate?
Yes.
Okay, thanks.
Yeah.
Okay, I think we can thank Carla again and move on to the next talk. So our next speaker is Anna McLeod, talking about can we learn something from resolved massive M stars in the...
Yeah, I'm not sure where that M was coming
there's
from.
an extra M, yeah. I'll let you introduce yourself.
Right. Okay. So first of all, I need to thank Elizabeth for basically allowing me to gloss over a whole lot of details, a whole lot of caveats in what I'm going to say in the next 15 minutes, because I will probably take up all of my time. The next thing I want to say before I start is that I will probably disappoint you if you are expecting to see lots of results. What I'm going to talk about mostly is work in progress. And also work that we want to do in the future. So this talk is more of a, this is what we're trying to do. If you're interested, if you have suggestions, if you want to collaborate, please come and talk to me later or drop me an email. And lastly, I also should mention that I started writing this talk yesterday. So the upcoming slides are going to be as new to me as they are to you. So let's see how that goes. All right, so if you are someone who's studying star formation in the very nearby universe, you might have, just like I have done many times, justify your observing proposals with some sentences along the lines of, oh, this particular galaxy or this particular star forming region is perfect to study because it is an analog of high redshift things that we can't resolve. Now then, of course, the question occurs naturally, do local analogs of high redshift galaxies exist? And I do appreciate that perhaps our concept of what is high redshift galaxy observations has perhaps changed since, you know, James Webb saw first light, because we're no longer talking about Z2, 4, or whatever, but we're going now to redshift 10 proper observations. Right. And why we ask this is because, simply put, properties of star-forming galaxies change as a function of redshift. And so here is just two examples. Again, I'm glossing over a whole lot of stuff here. But for example, what changes is the star formation rate to stellar mass relation, where at a fixed mass, the star formation rate increases as a function of redshift, right? But also what changes is where you end up on classical diagnostic line ratio diagrams, such as the BPT diagram. So we have to keep this in mind when we try and justify, oh yes, this particular galaxy at megaparsec distance is perfect to study high redshift galaxies. So really, the question then is, do we see local analogs, so local galaxies that line up with where these high redshift objects are? This is NGC 5253. It is one of those galaxies that we typically label as a perfect analog for the high redshift universe. It's a low mass galaxy. It has pretty high star formation rates. Particularly in its center, it has very high extinction, and it also relatively low metallicity. Now, if you compare or properties of this galaxy, such as its extinction towards the center, or its star formation rate and its stellar mass, to what has been observed with James Webb at different redshifts, then you would argue that perhaps, yes, this is a very good local analog. But of course, oh, here, yes. It also pretty much lines up within, you know, the scatter of observed high redshift galaxies in the BPT diagram. But of course, having said that, this is only one example, and it shows that perhaps these local analogs exist, but typically they have higher metallicity. So when we say, oh yes, this galaxy is a perfect analog because it's low metallicity, then, you know, these metallicities are not that low, let's be honest. And then there are a whole lot of other factors to consider. I'm listing only two here, such as there's a high degree of uncertainty in terms of what the escape fraction does as a function of redshift, but also galaxies in this mass bin, such as NGC 5253, might have been in very dynamically different states in the high redshift universe, and we observe them as isolated dwarfs nowadays. But assuming that these local analogs exist, then what we usually argue is, well, now I have my perfectly resolved galaxy. I can resolve individual star forming regions. I can determine ages, metallicities, star formation rates, a whole bunch of properties within this galaxy on a spatially resolved scale. And what I want to do is then make the jump to high redshift galaxies, which in James Webb, most of them do actually look sort of like this. And infer stuff about the high redshift universe by using these spatially resolved observations. Now, to do this, you might have to resort to using stellar population synthesis models, which come with all the caveats that Elizabeth already introduced. So what I'm going to talk to you about in the next couple of minutes is the opportunity that we now have with these very high resolution nearby galaxy observations to actually try and validate these SPS models. And these need validation, and here is why. SPS models work really well when you're trying to understand what a given property or quantity does if you vary it to the output spectrum of a galaxy. So this is just examples, these are screenshots taken from some of the BPAS pages, specifically Hoki, which is a very nice Python-based tool to interface with BPAS models. And some of the properties of galaxies have been changed here, and that results in different looking spectra. So in that sense, SPS models are very interesting. But if you try and do the inverse, which is starting from your integrated, so unresolved observation, and you want to fit your observed spectrum with models to infer properties of the galaxy, you encounter a whole lot of caveats and degeneracies. So going from going this direction, SPS models can tell you a lot of interesting things, but they're less certain and less useful, perhaps. Shoot me later if you want to use them in the other direction. Okay. So what we want to do is we want to validate SPS models via what I wrote here to be an apples to apples comparison. So you'll see in a minute what we do is we compare resolved and integrated observations to resolved and integrated models at fixed metallicities and fixed spatial variations, such that because we know what goes into the models, observationally speaking, we can then trust what comes out of them. And this is summarized in my current grant, which we have cleverly called the Spatial Resolution Project. It wants to do a whole lot of science that I'm not mentioning whatsoever here, but it basically uses very nearby galaxy observations to how should I put this? To study stellar feedback, massive stars, and all sorts of other stuff on a variety of different scales. But right now, I am only talking about one particular component of this project, and this is a work that my current postdoc, Bron Reichert-Chu, is working on. Again, there aren't many results that I'm going to be able to show you from what Bron has been doing, but stay tuned for more. Other people working on this on the smaller scales is my PhD student Bjarki, and then also working with Mark Swinbank and myself is Fang Li, who is working on high redshift galaxy observations that we then want to compare to. Okay. All right, so the workflow for this ground truthing or validation of stellar population synthesis models is as follows. Now, bear with me. We have a whole bunch of spectroscopic or integral field spectroscopy observations that are very highly resolved. And what we want to do is make the jump to the unresolved component here. So starting from spectroscopy and photometry of individual massive stars, we can do a whole bunch of things, such as, for example, and I will go into this in a couple of slides, such as, for example, determine ages of the star-forming regions these massive stars have formed in. We can also use the high-resolution photometry to perform CMD fits and therefore derive some of the properties that we're really interested in. So ages, metallicities, star formation rates, and star formation histories. And this is crucial now because what we can then do is we can pretend that we don't resolve the individual stars in here. So basically put an aperture around whatever specified size of region you want to. We do this for now on the scales of about 100 parsecs on the scales of giant molecular clouds. So we pretend as if we didn't have the spatial resolution. what? Okay, and we can go through a slew of determining, again, all these parameters, crucially using what we had inferred from the resolved stellar populations as priors for our unresolved property determinations. And that is how we are then going to be able, through the comparison of what we obtain here, to validate the stellar population synthesis model. So there's two tests that we want to perform. One is going to test the model inputs, and the other one is going to test the biases and uncertainties of the fitting routines. So we have already started working on this a couple of years ago. This is something I published now an embarrassingly long time ago, but it showcases what we can do very nicely. So with these resolved spectroscopic observations, here's just a very nice 3-color composite of the IFU data that we have of this particular nearby galaxy, NGC 300. We have already performed the very first step, which is to determine or classify individual massive stars at megaparsec distances. I'm going to skip over this because I'm almost certainly running out of time. But the point is that because we have the combination of high resolution photometry and IFU spectroscopy, we can actually do a pretty good job at deblending what in the IFU spectroscopy is basically crowded fields. Not going forward anymore. Oh, here we go. Right, fancy animations take time. Lesson learned. Of deblending what in the IFU spectroscopy looks like basically blobs, but in the HST high resolution photometry observations are clearly distinct stars. We have done this as a pilot project. We have identified individual massive stars in this galaxy. We have done a pretty good job at classifying them and at deriving properties using stellar atmosphere models. Here's an example of the Wolf-Rayet star. And here's just a color magnitude diagram. Again, I have to rush here a bit, so please do come and talk to me later. So this is a demonstration of the first part of the validation of SPS models. Okay, and we're currently propagating this to the full data set. We also have already performed the next step, which is determining the ages of the regions only based on the identified massive stars in here. This is taken from the paper. I'm not obviously going to go through the workflow of this particular work, but just to say that this does not use isochrone fitting whatsoever to determine ages. Isochrone fitting, in fact, underestimates ages of these regions. Also, we have tested what single stars and binary star models do to the results, and we find a clear plus point for the binary star models. Now, the good news is that NGC 300 is not the only galaxy in the sample. We are, as a matter of fact, going to tackle a whole bunch of different types of environments where to test stellar population synthesis models. Some of them are quite low metallicity, so truly closer to what we would assume as local analogs. And of course, these necessarily will have to be complemented with multi-wavelength observations and also confronting with simulations. So this is what we are currently working on. We are currently working on the unresolved component, and yet to come up is the crucial part where we confront the resolved properties to the unresolved properties and perform those two tests. So I'm almost done. The question originally was, can we learn something from resolved massive stars observations in the nearby universe? And I think it's fair to say that we probably can. These massive stars are bright, they're easily detectable. We can use them to validate models, even if the low mass stars in the same region are not spectroscopically characterizable. And why are they interesting? Well, of course, they are the sources of escaping photons and the sources of stellar feedback, which are crucial ingredients to our understanding of the high redshift universe. I will probably just leave you with my summary and not read it to you and let you read it on your own. So thank you very much.
Thanks very much, Anna. Unfortunately, we've run out of time for questions, so you'll have to ask Anna questions in the lunch break. But good news is that's coming up very soon. Our last talk before we go for lunch is by Connor Byrne, who's going to be telling us about the effects of changes in the alpha to iron abundance ratio.
Thanks, Alex. Yeah, as Alex pointed out, we're just running up for lunch, so I will do my best to keep things short because I'm sure you're all hungry. How does alpha enhancement affect the evolution of massive stars? Good question. I think Surdeep, I think, showed this earlier, so I don't need to explain it in a huge amount of detail, but why do we care about this in the first place? It comes down to the chemical evolution of the universe and the fact that things don't necessarily behave the same. So to take an example, you get oxygen. Most of the oxygen buildup in the universe is from core collapse supernovae, and that happens pretty rapidly. But if you look at something like iron, most of the iron comes from type 1a supernovae, and you can see that this doesn't really kick off until a bit later because that comes from low mass stellar evolution, and therefore it takes longer to get started, which means if you do the sort of a rough comparison with a couple of arrows, you can see that compared to the present day, if you assume that these are sort of equal height arrows, if you go to earlier times, the ratio of oxygen to iron changes as we go back. This is something that we see observationally. If you look at as you go down in metallicity, the ratio of oxygen to iron goes up. You see this in these high redshift galaxies here, these blue points, and also in stars in the Milky Way, in the halo and the disk. So this is a process we know is going on, and it's something that we need to make sure we're representing properly in our modeling techniques in order to actually interpret the data correctly. Elizabeth introduced population synthesis quite nicely earlier, so I don't need to go through this in much detail either. But in terms of the general principles of BPAS specifically, as we mentioned, you go from stellar evolution models, you do a population synthesis based on an IMF assumption, your binary parameters. You then do spectral synthesis by assigning spectra to each of the stars in your stellar population, and you get your outputs here. So you get your spectra, your colors, and all of the other interesting things that you can get out. And how does all of this change if you change your assumptions on how the alpha element abundances change? This is something that we looked at in some of the spectra recently, which we saw some results presented earlier. But the big question, considering it's the first step in this whole process, is how does this affect stellar evolution? So that's something that I've been trying to explore recently. And what we've done is we've got a large grid of stellar evolution models covering, the full sort of range of stellar masses, a broad range of stellar metallicities, and importantly, varying this alpha to iron ratio, using several different ratios, done detailed stellar evolution models. The work with single star evolution models has been completed and was published quite recently. So I'm going to show some results from that. Binary models, as I'm sure you understand by now, are a bit more complicated, and there's a lot more physics and also a lot more models required. So this is still a work in progress, but I'll try and show some preliminary results. But to look at single stars for a moment, what happens if we assume a fixed total bulk metallicity, but we change the alpha to iron ratio? Okay, so a few things happen. Well, a lot of things happen. I'm going to pull out a couple of key ones. One is we find that low mass stars have shorter lives. This is illustrated in this plot here, where we're looking at basically log of the stellar main sequence lifetime compared to a reference value for a certain composition, and how that changes with mass on the x-axis here. And you can see if you compare a low alpha value up here in the blue colors versus the yellow colors down here, at low mass, you find that actually low mass stars, and we haven't talked much about them, but low mass stars have shorter lives compared to their solar scale counterparts. This is true both at solar metallicity and if you go to a 10th solar, although the effect is less pronounced. Most stars across the mass range tend to be hotter. You can see this basically here in this panel on the top. If you look at these stellar evolution tracks for 10 solar mass star, If you increase the alpha to iron ratio, you go from here across to here. And so across the main sequence lifetime of these stars, they tend to be bluer and hotter, so you would expect more ionizing flux, which is important for a lot of things that we've discussed today. And thirdly, a slightly subtle effect, but important nonetheless, is that if you look at the radius of these stars as they reach the end of the main sequence, you find that alpha-enhanced stars, which again is this sort of yellow color, have slightly smaller radii than you would expect for a typical solar scaled star at the same composition. And this may have an impact on our binary interactions. If these stars are more compact, then maybe they interact slightly less, and then that leads me to, that does not lead me to, I forgot about this slide. Okay, one thing that we can say from this is if we look particularly at Wolf-Rayet stars, is at what mass do they form at? And this is something that the minimum mass of a Wolf-Rayet star, or the initial mass of a star that forms one, is predominantly dependent on iron. And you can see this here where we've plotted the same data, the minimum mass of a Wolf-Rayet star on the y-axis, but in each panel, we're either varying the iron abundance, the oxygen abundance, or the total metallicity for our different assumptions on alpha over Fe. And if you look, if you match on Fe over H, you see they all fit nicely on this trend. The stars only really care about iron, and that's because the main process is your wind stripping and your mass loss, which is proportional to iron in the first instance. However, if you look at oxygen, so it takes, for example, an oxygen abundance of 8 log abundance, you can see that you could vary the minimum mass of Wolf-Rayet star could come from 30 solar mass stars, could come from 120 solar mass stars, depending on what the oxygen abundance is. So this indicates if you don't know what the iron abundance is, you could be drastically under or overestimating the amount of Wolf-Rayet stars in your stellar population, the contribution they're making to the ionizing flux. What does this mean for binaries? Because this was really the single star results. So just to quickly sort of summarize that, we said low mass stars have shorter lives. This is going to affect your delay times on your 1A supernovae. So maybe you get slightly faster iron enrichment than you would naively expect. Stars are hotter and bluer, so we're going to get more blue flux. But massive stars have smaller radii, which might mean that we get fewer binary interactions, which tend to produce more blue flux. So these 2 points kind of compete with one another and counteract each other. So we really need these binary models to address this. And so that's where I'm just going to show a couple of preliminary results that we have from the initial runs of our binary evolution grids. So there's a lot going on here, so I'll try and talk you through it. But we've got two figures. So this figure here is for Z equal to 0.001, so that's about 5% solar, and the alpha over Fe ratio is 0. So this is a solar scaled model. And on the right, we've increased alpha over Fe by 0.4 dex. And then you've got 4 separate panels. So this is the, each panel represents the companion mass, or the mass ratio of the companions to our stars. So a extreme mass ratio system all the way up to something which is near equal mass components. And then the initial mass of the most massive star in the system is on the x-axis, and the initial period is on the y-axis. And we're coloring this based on how much mass the secondary star gains during its lifetime. So if it gains no mass, we assume these stars haven't interacted. If it's gained some mass, which you see, for example, in these sort of the green areas, then we've had some sort of mass transfer event during the evolution. And you can also get these black points here indicate where we've had stellar mergers. So the two stars have come together and formed one. And so the main thing to consider is if we compare like for like, so we look at this panel here versus this panel and so on and so forth. I should also point out there are several areas where some of our models still need some more work to actually get them completed. So that's these red points here, and you can see that sort of mugs up some of the areas of this diagram where maybe the color scaling isn't quite right, but we'll get there. But the main thing I think that I can notice is if you look at the mass ratio of 0.4 systems, if you look at this region here where we get stellar mergers, this tends to extend to higher masses and higher initial periods where you still get these interactions. So if you go to an alpha-enhanced binary star population, this sort of effect, you're going to get mergers at higher masses, you're going to get mergers at wider periods. So overall, you're going to get more stellar mergers, more binary interactions, And in this sort of mass regime of the sort of 50 to 100 solar masses, that means more ionizing flux. So you would expect perhaps we're going to get more ionizing radiation from a population like this. So I'm going to try and wrap things up on time. So to summarize, I mean, the main points are changing the alpha to iron ratio has a measurable impact on the evolution of massive stars. That's both in terms of isolated stellar evolution, but also in terms of their binary evolution as well. Obviously, you've got some way to go to actually get some solid conclusions of this, but the preliminary results from the binary model suggest that we're going to get stronger ionizing flux if you've got an alpha-enhanced high redshift stellar population. So obviously, this is something that's quite important to consider when we're comparing our SEDs and our observations to models. And I'd also just like to take this opportunity, since I have a couple of seconds left, to point out that we're organizing a session at NAM on looking at stellar populations and chemical evolution across cosmic time. Some of the organizers are in the room, but if anyone's interested in coming, don't forget to send an abstract or come along. All right, thank you.
Thank you very much, Connor. Do we have questions for Connor?
Could you just remind us why low mass star live shorter with a higher alpha to iron?
Yeah, sure. So the main effect here is again, it's because if you've got a fixed total metallicity and you increase the alpha element abundances, you've decreased the amount of iron in the system. And the iron has a significant contribution to the stellar opacity, so these stars would tend to be more compact, and that increases the nuclear reaction rates and things like that. They're hotter, so they burn through their fuel faster, essentially.
If you change carbon abundance as well, would you expect CNO cycle can change the situation again?
Yeah, probably. I don't know how, but I would expect probably not as significant an effect, but I don't know. But it's definitely something to consider. Yes, I mean, this is this simple. You change all the alpha elements in tandem, but obviously the actual picture is a bit more complicated than that. So yeah, there's probably some second order effects in there as well.
Take one last question before lunch.
Is there a problem with globular clusters? So if you have this half the lifetime of the stars for the low mass stars, globular clusters are alpha enhanced. So should we think the globular clusters are half as old as we thought before, or how should we apply this?
Yes. So there's probably an indication here that perhaps this would impact your age estimates, yes, of globular clusters. If these low mass stars live shorter lives, then they're probably a bit younger than you would anticipate if you fit a solar scale model. Whether that's physics breaking for your understanding of globular clusters, I'm not sure. I think you probably know better than me. We could talk about it maybe over lunch. But that is something, and something I didn't flag up is this sort of this alpha sensitive lifetimes is something that's important if you're running things like analytical pop synth models where you're applying simple equations. You only care about the total metallicity, but actually if there's a second order effect here due to your abundance ratios, then that's something that needs to be taken into account in order to fully encapsulate the behavior that's going on here. But yeah, that's a good point. You'd expect that your globular clusters are younger than you currently think they are, if these results are correct.
Very interesting, thanks.
Okay, let's thank Connor again and all of our speakers from this meeting.
Right. Good.
All
Yeah.
good. That's me.
Amazing. Cool. Then welcome back, everybody, for the post-lunch session. This is much shorter, so I think we should hopefully end by 3:30 and then have another half an hour left for discussions over coffee. So yeah, let's kick things off, exactly where we left them. More massive stars and more spectra. So now we've got an invited talk, so 30 minutes long, from Paul Crowther, Properties of Metal Poor Massive and Very Massive Stars in the Local Universe.
Thank you. Right, so so I'm going to be very much focused on the local universe, and I generally metal poor, and I'll try and define what I mean by local and metal poor in a moment.
So I'm very much a stellar astronomer, so I couldn't avoid showing some beautiful spectra from Ulysses and the UV, which is this large Hubble program that's just recently completed of massive stars, which half of Ulysses involves massive stars in the clouds. And then there's complementary optical data set, complete optical, which Yorick coordinated. Okay, so when I talk about local universe, what do we mean by that? Well, so if we want to be really local, when we can actually resolve medium brightness stars, and we're looking at certainly the clouds and maybe a little bit beyond the clouds, and our kind of poster childs of metal poor star formation in the nearby universe are the clouds, particularly the LMC, also a few bits of regions in the SMC. If we go to kind of megaparsec distances, then we're kind of more in the kind of cluster era, where a cluster which we can resolve in the clouds is a splodge, even with a high resolution at a few megaparsec. 1/18, I'll touch on a bit later on. And then what other people might think is local might be things like, for example, here this is a green P galaxy at redshift 0.3 from Sloan, which is metal poor, quite a high star formation intensity. And then here's an example of I'll show a spectrum or predicted spectrum of it later on. This is one of the clues galaxies. So this is again metal poor at where non-zero redshift. So when I talk about local, I'm mostly focused here and a little bit of kind of things at megaparsec distances. When I talk about metal poor, and again we've heard already that we have to be careful when we talk about metallicity because we tend to use oxygen as our proxy for metallicity. Yeah, so these are the clouds which current metallicity indicators say are in the 8 point something, so moderately metal poor, and that's true of other. This is now distance modulus because I'm a stellar astronomer, which means basically these things over here are 10 magnitudes fainter, and so therefore 10,000 times fainter for a random star, and angular resolution wise going from 100 kiloparsec to 10 megaparsec, of course, factor of 100 for spatial resolution. So these are kind of our very nearby. This is star formation rate or H half luminosity. So high star formation rate, low star formation rate, and generally this is a reasonably complete looking at metal poor galaxies in the local group. And of course, if we then go down to our more metal poor by way of proxy of oxygen, these red ones, 1613, we've seen a little bit of 2366. We'll talk about that one too. And then if you want to go to I would say really metal poor in the local universe, we're looking at things like Sextans A, which has got a pretty puny star formation rate. If you want to have a more impressive star formation rate, you've got your 1/18s, which is very metal poor and only about 15 megaparsec away. Okay, so most of my talk is actually on the ionizing photons that we see in those beautiful James Webb or nearby star formation galaxies in terms of nebula diagnostics. Yeah. So since there were some PhD students in the audience, can't we just see it? Yeah, and we can see it if you don't mind looking at things which are within 100 parsec of the sun, where you don't have much column density of hydrogen. And so there's very few places where we can look at early type stars directly in the Lyman continuum ionizing photon rate, below 912 angstroms or above 13.6 eV. But that's a handful of B stars basically in that regime. Indirect, well, basically where you have a nebula associated with ideally a single star, you can do kind of a Zanstra type model where you can then say, well, the nebula sees all the ionizing photons, even if we can't directly. So you can do an indirect way of looking at it. It's hard when you have a mixed population, star forming region. We have lots of OB stars. It's easy if you have a single PN central star or like a Wolf-Rayet. But in general, 99.999% of cases, we don't have the nebula for a single star or direct observation. So we have to rely on predictions from your favorite model atmosphere. And that can either be matching parameters from evolution models, we heard about those earlier, or trying to fit a UV optical or infrared spectrum of an individual star. And depending on what kind of parameter space we're dealing with in terms of gravity and temperature or wind, you can pick up your favorite model. Okay, so if we start nearby, as in really nearby, we can resolve individual stars. So essentially, if we want lots of ionizing photons, this is the HI diagram. So 0 Kelvin, 60 kilokelvin, 10 to the 3, 10 to the 7. If you want lots of ionizing photons, you need to be in the upper left part of that HI diagram. Yeah, because you've got high luminosity and you've got a hot thing. Yeah. So the real key players in terms of normal stellar populations are O stars, which are the most common. B stars are pathetic in terms of ionizing output. Sorry, B stars, but they are. O stars are the most popular, most common. If you want to have a really hard, potentially really hard ionizing output, you need your kind of classical Wolf-Rays, which are the evolved descendants of O stars predominantly, which are much hotter, but have a much shorter lifetime. And we also touch on briefly the things that we categorize as very massive stars, which have masses above 100 or so. So on the O stars, this is a WM basic model from a couple of decades ago that I did with Linda Smith, where we're looking at basically the ionizing spectrum. So again, now we're doing an energy. So alignment, this is now our 30.6 eV, anything to that. So anything blue here is hydrogen ionizing photons, red is helium-1, and there's hard ionizing photons are in green, Q1, Q0, Q2. And these are all kind of essentially, if you want to have a healthy ionizing output in say the helium-1 ionizing continuum, then you need a pretty hot star. So these are 50 kilokelvin, which more or less maps into a 75 solar mass star on its main sequence. If it's much cooler, it's a relatively softer spectrum, and if it's a borderline B star, it basically ain't got much going on. Okay, so normal O stars have a good fraction of their lifetime. Yeah, 90% of their lifetime as more or less spent as an O star, but I would say it's kind of soft to medium. They get a little bit hotter as you go to more metal poor environments because of the opacities differences, but relatively soft or medium at most. Okay, so then there's been a lot of interest already in Wolf-Rays. We heard that today already. Now, of course, your classical Wolf-Rays are the evolved descendants of these O stars, so therefore it's that helium burning phase. At most 10% of a life. So A star isn't a classical Wolf-Ray star for its entire life. So in the tail end of its evolution. But if we take again example of a solar, this is a hot WN star, which has got lots of nitrogen in the spectrum. It's a relatively soft spectrum, at solar composition, because you have strong winds, and it's been known for several decades, work from Werner Schmutz 3 decades ago now, that the strong winds suppresses the hard ionizing photon production. It's only if you crank down the mass loss rate and somehow can still produce a Wolf-Ray, just to strip the star off, then you can get pretty hard ionizing output. This is the red one here, is something I did some time ago, which was basically cranking down the mass loss rate and metallicity, and you get a pretty hard spectrum. If you can produce such a star in an evolution prediction, that's a whole different story. But if it can exist, they're pretty hard. Yeah, relatively hard. That's true for WNs and WCs. It's a similar story. The strong winds at high metallicity has a relatively medium spectrum, but if you want a hard spectrum, crank down the mass loss rate and metallicity. And actually, those WC stars would actually be seen as WO stars because of the nature of the classification of those things. These are predicted. Okay, these are predicted. Let's see does anyone actually ever see nebula helium-2 coming from Wolf-Rays? Yes, the answer is most. When you have this is nearby universe, local group, there are very few nebula ionizing photons coming from massive stars. Most of them come from Wolf-Rays. I've got 3 pretty pictures, and 2 in the LMC, 1 in the SMC. This one, if you like spectra, this is the stellar spectrum, broad Wolf-Ray emission lines, the WO actually, and then nebula helium-2 sitting on top of 4686. So we do see nebula helium-2 coming from Wolf-Rays, and that gives you some confidence that the predictions have some connection to reality. Okay, but as I mentioned earlier, to have a metal poor Wolf-Ray, we have this a direct route where you have this wind self-stripping, or in the binary where you have mass being dumped from the primary onto the secondary, and that is known to be metallicity dependent. Yeah, so in the Milky Way, minimum luminosity of Wolf rays is about 10 to the 5. It's about 10 to the 5.6 up in the SMC, and you imagine it would be even higher in more metal poor environments. SMC is only 1/5 solar. Yeah. If you like nitrogen, you can basically get nitrogen enhancement produced into the ISM coming from the Wolf rays, particularly in the WN phase. We do see it in some Wolf ray nebulae. So that's in the local group in terms of Milky Way, LMC, SMC. We do even see Wolf ray bumps, albeit somewhat weak, in 1 Zwicky 18. This is our 1/30th solar composition nearby star-forming galaxy at only 50 megaparsec. It's been known for several decades that we see nebula helium-2 and nebula helium-2 in the optical and in the UV. This is from Sally Heap's COS data set. And we see bumps that look like Wolf rays in the visible. So we can somehow produce Wolf rays even at log O2H down at 7.2. How they do it? That's a question we don't know, but we see them, so therefore nature finds a way. Okay, so Wolf rays, if it's a classical Wolf ray, it's spending at most 10% its helium burning phase as a Wolf ray, which can be very hot and can be producing a relatively soft medium spectrum in metal-rich environments, or medium hard in a low metallicity, which is the kind of environment that many James Webb galaxies we see are. Okay, so how can those are our standard O stars and Wolf rays from normal stellar populations. How can you boost the ionizing photon production? So here's some work from a couple of decades ago from Ines Brot, and we're working with Norbert Langer. And this is now our standard HR diagram where you have basically stars evolved to the red. Yeah, but in the SMC metallicity models for single stars, if even at intermediate masses, I'd say, not very high masses, if it's rotating at a very high fraction of its critical, evolution can proceed directly to the blue, whilst in the main sequence. So you could, in principle, if you have a really fast rotator, then you can end up with a pretty hard ionizing spectrum for much longer because it's the main sequence evolution, not the post-main sequence evolution. You also get, because you have basically what we call chemically homogeneous evolution, you get basically the entire star is essentially the core, and therefore at the surface we see the projective CNO cycle, which is nitrogen enrichment, which someone like to see lots of nitrogen enrichment. But that requires, I would say, pretty fast rotation. Do we see such fast rotation? Well, Bloom is this survey that we mentioned earlier, where we're looking at about 1,000 OB stars in the SMC, multi-epoch data. Half of them are apparently single. And so if this is your kind of prime channel for producing hot, nitrogen-rich, plenty of ionizing photons coming from the main sequence stars in the SMC composition, these things should be going at hundreds of kilometers a second. In reality, they peak at about 100. Well, V-Sin-I is peaking at 100. Yeah, so there are a few apparently fast rotators, but that's not going to produce a whole population. Yeah, it's going to be the oddballs might do it, but in general, you're stuck with things evolving to the red, which is in terms of ionizing photon production is no good. Now, this paper from Grace Telford this last year, looking at these metal poor stars in more metal poor galaxies. So these are DOP, Sextans A, WLM, down at below these two below 10%. Now 200 isn't 500, but it's of these three stars, two are quite relatively fast rotators. So there's some hint on this very small sample that there's maybe faster rotation in a more metal poor environment than the SMC, possibly. So rotation is in principle, in theory, a good route to producing these hot things. In practice, I'd say observationally, not really. But if they were existing, then you can have most of a lifetime they're going to be fast rotating and producing a relatively soft, but up to medium, a relatively high mass at low metallicity. This is unique to low metallicity. Okay, so how else can we boost the ionizing photon production? So if it's not just the single stars doing their thing, it's not just initially fast rotating single stars, binaries can be our friend. So it's been known for a long time that if we basically have two stars close enough together that they interact, once the primary floats up, for its Roche lobe, dumps its envelope onto the secondary, you have a stripped, more massive primary. Stripped means hot. That sounds good. Yeah, so this is our from Ilva Gertberg's work, a 12 solar star that basically starts the main sequence here, and then if it's single, it dies as a boring old red supergiant. Yeah, but if it's in a binary, if it dumps its envelope onto a secondary, then it strips, this primary is stripped, and it basically ends its life over here. This is, again, the blue stuff is lots of ionizing photons, which is what people like. Yeah. So the mass donor produces lots of ionizing photons. The mass gainer, well, of course, it has, you're dumping the atmosphere from the primary onto a secondary, and that spins up the secondary. So your secondary is spun up. These are some works from some of the Mink, and your fast rotating secondary. So you might think that's probably not doing much by ionizing photons, but you get lots of nitrogen. Fast rotators produce lots of nitrogen. So that might help in that regard a little bit, perhaps. And now, so the question is, okay, well, that's what you get from, these are all theoretical predictions, but is there evidence, empirical evidence, that we have lots of close binaries in metal poor populations? So this is the work that was mentioned earlier from Sana and Milky Way, saying that intrinsic close binary fraction is about 2/3-ish. This is work in the tarantula in the LMC, also from Sana. This is our new data point for O stars in the SMC from Bloom, and it's more or less flat. You know, we don't know what's going on well below a 10th solar, but between solar and the SMC, we have lots of close binaries. Yeah, so the theory says that's great, because in that case, we can then predict what you might expect in terms of the nature of the stripped primaries. And so again, more work from Ilva Gertberg showing that as you go from a stripped star in the metal poor, which is now down at what's that? 1/10th solar, 1/7th solar, SMC like. If you go to like a 6 solar mass stripped helium star, this top curve here, you know, it's producing, I would say, you know, certainly plenty of helium-1 ionizing photons and a few helium-2 ionizing photons too. Yeah. And again, these are all predictions. Do such stars exist? And it turns out they do. So this is a kind of a color magnitude diagram of the LMC and SMC. This is the main sequence is marked on here. So anything to the left of the main sequence is hotter than main sequence stars. Wolf-Rayets are up here at the top, yeah, because they're quite bright. But these things with labels on are some of these stripped stars which Ilva Gertberg and Drought have observed in the clouds. So we do know they exist. Might not exist in the numbers you might want them to exist, but they do exist. And in fact, this is more of a ionized, this is now using not so much the models, but using the real stars, which we've analyzed. And we found that basically, yes, these are, you know, their total hydrogen continuum photon predictions relatively modest, but actually it's pretty hard, you know, plenty of helium-1 ionizing photons, and, you know, not too shabby by way of nebula helium-2 as well. There is a proviso. This is some work that, again, which Ilva's been involved in, which basically says, well, more metal poor, therefore more compact, therefore not so easy to basically bloat up to a point at which you can get the atmosphere being stripped off the primary onto a secondary. So in a very metal poor environment, actually, unfortunately, there's more massive, you know, lots of ionizing photons. It will go from relatively high in the solar environment to much, much lower because of the nature of the strip of the primary at the point at which you may want it to be stripped by the companion. So again, strip stars, yeah, unfortunately might be rarer, but modesty. Okay, what other hot stars might there be? So this is again a model of a star. This is a star itself. It's pretty hard. You might go, hey, we want lots of these things, don't we, to produce these, what we might see at high redshift or an extreme galaxy at low redshift. So that's the good news. The bad news is they're pathetically faint because that was an evolved low mass star. That was a very brief phase right at the end of the evolution of a low mass star. Yeah, so their total, this is now on the same scale as a common or garden O star. You know, it's a 2 orders of magnitude less luminous, therefore it's hard, but it's incredibly faint by way of luminosity. Yeah, so unfortunately, they ain't going to win, especially if it's a young galaxy which hasn't had a chance to produce such stars yet. So just in the last couple of minutes, I want to kind of touch on, okay, that was looking at individual stars and predictions. What about populations? Yeah, is there anything nearby that's got a relatively impressive star formation rate? So I would say Tarantula is our poster child of resolved populations, where it sits in the kind of same region in the N2H alpha O3 H beta diagram as the green peas. So it's not extreme, but it's green pea-like. Wolf-Rayet bumps, high, strong O3, strong H alpha from the integrated Muse data we have. This was touched on earlier, that if you look at this is, you know, tens of parsec. If you look at all the OV stars and you build up your mass function, it's at 2 sigma level, it's somewhat top heavy compared to Salpeter. So that's suggestive that it's you know, there's some evidence, empirical evidence, that you have a somewhat slightly top heavy IMF. Just in the last minute or two, if we now look at the central cluster in that Tarantula Nebula in the LMC, it's been known for a long time, this is my textbook from Mayday, that basically, if you go to really massive stars, there's Strip Eddington, can't exist. Feiger said the same from looking at the Arches cluster. Unfortunately, the theory is a little bit more complicated. If you go to very massive stars from work from Yusuf, and right in the heart of that cluster, we've seen stars which are Wolf-Rayet-like, because you have strong winds, with high masses of up to a few hundred solar masses. But they're more luminous, but they're not really hotter than O stars. They have a strong wind, so that's probably true going on everywhere because they're so close to the Eddington luminosity. So what do they look like in the ionizing spectrum compared to our common garden O dwarf? Well, they're much more luminous because they're of order 10 times more luminous, but they're not really any harder because they have a strong wind, and strong winds suppress the extreme ionizing output. We do see evidence for them. They have a strong stellar 1640 emission. We do see that even in metal poor galaxies, like this is Markarian 71, where we see this broad 1640 emission. This is a young cluster. That's a few megaparsecs. So we see evidence that this is true, that we do see very massive stars in integrated light of clusters in the nearby universe. But in terms of solving this ionizing photon budget problem, well, they basically are medium, but they are very, very hard, but not high velocity, but not hard enough. And this is a problem when we look at both nearby galaxies, extreme galaxies, and at high redshift, where basically people have to lob in a black body, a hard black body, a little bit like that PN central star, to basically, to reconcile what we see by way of the nebula helium-2 and carbon-4. So, in summary, the kind of stuff we see, so what produces the ionizing photons? Well, it's O stars. If you can get a classical Wolf-Rayet, WNs and WCs. If you want a hard output, then the classical Wolf-Rayets, I would say, are your friends, as are stripped stars. Can you help with other effects? Rapid rotation can help, but we don't really see evidence for it empirically. And then, of course, we have other possibilities like high-mass-X-ray binaries and shocks. And there's been a couple of papers there from Garnett and Peter who've talked about that. So without further ado, thank you.
Thank you so much, Paul, for that amazing overview. We have a few minutes for some questions.
Thanks, Paul. I learned a lot. If, like me, you're interested in what the massive stars do to their environment, the question is not only about what the sources are of the ionizing photons, but also when they are. So in your table with the various sources, how would...
So if by way of when, if it's a single, but if it's a cluster, then of course we're looking at on the main sequence, it's O stars, or fast rotating O stars. But essentially it's main sequence stars. These things are also true, but they're still rare. In a normal cluster, you might get none or one. Yeah. So in the main sequence, it's all essentially it's O stars. After the main sequence, I would say it's initially classical Wolf rays and ultimately stripped, because these things have a mass limit. I would say these things go down. The helium stars go down. You can have these coming at 100 million years after the burst.
Yeah, exactly. So that was kind of my question, right? Because the strip stars become important at much later stages.
Right. Yeah. So I would say after after tens of millions of years, the only source I would say of the main the main source of ionizing photons are strip stars. After once all the Earth stars have died, and it's the Earth stars responsible for what we call classical Earth stars, which are essentially helium stars, but just massive helium stars with strong winds.
We've got another question here.
Paul, fascinating stuff. You asked a question about whether any of those stripped stars have been found. Actually, I think they might have been, but it would have been quite easy to miss it because there was a paper just over a year ago.
Yeah. So these are the strip stars that we've seen in the clouds.
Right.
But so essentially, these aren't normal stars. These are Wolf rays. These are strip stars in the clouds.
But there's one that looks like it's actually a stripped helium star.
Yeah.
And it fits very nicely into the Gottberg spectral catalog.
Yeah.
But it has one extra feature.
Yeah.
It's a very strong supersoft source because it's a binary, and there are several of these in the Magellanic Clouds now that we're finding with longer periods, indicating the donor has to be much bigger.
Yeah, so I would say I didn't have time to go into details of strip stars, but I would say there's three types. Is where the optical light is dominated by the strip star and not the companion, because these are in binaries, of course.
Yeah.
Yeah.
Of course.
There's the ones where you have some contribution from both components in the optical. I mean, the hot star, the strip star in the UV is dominant, but in terms of optical light, some have a mixed from a hybrid spectrum of a normal star companion and strip star. And in some cases, it's the companion star that still dominates, because again, you have such a variety of possible masses of both both strip star and companion star.
The key point here for you is that the accreting white dwarf is capable of actually outshining the donor by a long way in the UV. And that, I think, is what you're looking for.
Yeah. So all these ones. So okay. So all these ones are where basically you've got the blue ones are where essentially your optical light is dominated by the helium star, and the green ones are where it's composite, and then the pale green are where it's dominated by the companion. That's why the different colors are indicated there for that subset of strip stars in the clouds.
So we'll just take one more question, I think, from Alex.
Paul, thanks for the really nice talk. Just with you mentioned at the end the very massive stars. So that was for showing this relatively softer spectrum. That was for the LM. This is in the LMC.
This is currently the most massive star we know about that we've been able to kind of have a good idea about its luminosity and mass. Yeah.
So I mean, when you showed earlier the Wolf-Rayet stars, get harder at low metallicity. If you went to sort of 5% solar metallicity, 1% solar metallicity, would you expect this to also get harder?
Sure. Yeah. Absolutely. Yeah. I can only show you, in this case, I can show you ionizing predicted spectrum of a star that I know exists. Now, do they exist in metal at what point at 1% solar? I would say absolutely they'll exist. Anyway, you've got a lot of gas that's basically producing a lot of stars. I would say they exist. I think on the main sequence, they will be hotter, as all massive stars are. As you go to metal poor environments, they're hotter, so they'll be harder. But if you go to the extreme, actually, they will still be up against the interlimit, which means they'll have a relatively strong wind, and so probably suppressing the hardest ionizing spectrum. And what we also don't know is actually what they do once this is the main sequence star. What they do after the main sequence, they probably lose a lot of mass, and then but if a metal poor one would lose less mass, and therefore would still remain quite luminous as a helium star. So I think they're few in number, but where they are, I would say they're major players. These things contribute a non-length fraction of the entire Theta Doradus ionizing output, maybe 30%.
Can I just use my chair privileges to ask you very quickly to comment on maybe high mass X-ray binaries?
You can, yeah. So one slide I just prepared, didn't show, was this one from Peter from a couple of years ago, where again, if you want lots of hard ionizing spectrum, then these are your normal stars. This is from BPAS for a particular star formation rate. What's that, 1/5 solar or something? And then this is essentially what Peter did with looking at potentially a population of X-ray binaries, and of course they peak in the X-rays, as they're clear in the name, but they are tailing off as you get towards the kind of helium Q edge. So his view was not a dominant contribution, but not a dominant population.
Cool. Let's thank Paul again. So next up, keeping in the tune with very, very massive stars, we've got Yorick Vink, who's going to tell us about chemical and ionizing feedback from very massive stars.
Yeah, thank you. Yeah, let's stick to very massive stars. So basically, talk a bit about chemical enrichment at the end of the talk and a bit about the ionizing radiation. Basically, if you want to understand the IMF, it is good to have not just one bit of info, but have both bits of info. And hopefully from the combination of the chemistry and the radiation, we can eventually work out what the IMF is in the early universe. So if you forget the talk, let's at least remind yourself of this talk. So basically, what I'm going to show you is that for very massive stars, the more massive stars, so this is mass versus time, if you observe very massive stars at maybe 1 or 2 million years, they might be observed at only 200 solar masses, but whether they were initially 200 or 1,000, we just cannot tell, because the mass rates up here are much higher than down here. At some point, when you work up the mass range, the mass rates become so high that that even, I think, when the star is forming, we always assume that we know T equals 0. We obviously don't. In reality, these winds will already start blowing during the main sequence, in the pre-main sequence. And when they exceed the mass accretion rate of 10 to the minus 3 solar mass per year or so, then that may well set the upper limit to stars. So I would argue that the upper mass limit will be set by stellar winds, and that at lower metallicity, we will actually have higher mass stars. So this is different from the physics that Matthew Bate discussed this morning. We all know about the cooling. At low metallicity, you have less cooling, and therefore you have more massive stars. Well, 3 stars could be more massive, but I think what we are seeing in globular clusters, for instance, and in other elements of the universe, that we see an IMF that is shifting. So we shouldn't just look at the slope of the IMF, but also what is the cutoff limit. Okay, that is basically the bottom line. So now the talk. What is a very massive star? So normal massive stars are between 10 and 90 or so, but the very massive stars are very different because the Eddington factor is much more dominant. And this Eddington parameter, basically the L/M ratio times some opacity, has 2 important effects for very massive stars. It affects the structure of a star. When you get close to the Eddington limit, the star wants to inflate, and it wants to drive a very strong mass loss. And the strong mass loss wants to make the star blue. So you have 2 physical effects. One wants to make the star red, and the other one wants to make the star blue. Very massive stars are a bit different from supermassive stars. These are 10,000 solar masses or so. We still don't know if they exist, but the very massive stars we know exist. So we have your normal O stars. They have quite a lot of ionizing radiation, as Paul showed, but still not as much as the Wolf-Rayet stars, the evolutionary consequences of these stars. Basically, what we want to consider is these very massive stars at 100 and above, and how these compare to your more stripped stars, your helium stars. They can either be optically thick as Wolf-Rayet stars, or they can be optically thin as stripped helium stars. Now, the developments we've seen, of course, is that they might be important in the early universe. If you have 100 solar mass stars here at high redshift, then we want to know, can they have contributed to the reionization of the universe? And these stars may well have been important in driving the evolution towards what we see today. And we may not have local analogs in terms of galaxies nearby, But in terms of the stars in the clouds, as SMC, 20% solar, we can already study individual stars at 20% solar. And I think that gives us a lot of interesting physical constraints on what the early universe stars will be like as well, even if the galaxies are somewhat different. There have been claims when people seen helium-2 emission that these might be population 3 stars. They must be very hot to produce this helium-2, but that might be controversial, even the detection, but that's another matter. The point is that these helium-2 lines might also be produced in other ways, and I'll come back to that. And then we have seen the chemical enrichment has already been discussed. Nitrogen excesses, supersolar nitrogen in redshift 11. So that means much more nitrogen than commonly assumed. Now, what causes that? Still being debated. Rotating Wolf-Rayet stars might be one option. The problem is we haven't seen rotating Wolf-Rayet stars yet. Supermassive stars, again, might be hypothetical, but very massive stars could do it. We know they exist. We know they produce the helium-2 emission in 30 Doradus, and they can produce lots of nitrogen. Actually, one very massive star, in the LMC in this case, can produce, via the CNO cycle, about a solar mass of nitrogen, pure nitrogen. So these stars can produce a lot of nitrogen per individual object. And in addition, when they produce the CNO, the nitrogen during the CNO cycle, you also get additional cycles going, and they may also be relevant for sodium and aluminium and so on that are seen in globular clusters. So what is it that we need my question is, what is the biggest star in the universe? What is the most massive star in the universe? How are we ever going to find out? And I'm not talking about the number, but what is the physics that sets it? And I think by looking at two of them, the ionizing flux and the chemical yields, we can potentially work this out. But for that, we are going to need consistent stellar evolution models. We still do not have consistent stellar evolution models where the mass loss rate that goes into the stellar evolution is the same as the mass loss rate that goes into the atmosphere models. So that is what we want to construct. And for that, we need hydrodynamically consistent atmosphere models. Most people, when they use atmosphere models, they infer the mass loss rate from the observations, or they infer the luminosities and temperatures. But what we want to do is we want to use these same photons to drive the wind and to tell us what the mass loss rate actually is. And there are several ways of doing this, in co-moving frame calculations or Monte Carlo methods. And what we can find is because the winds at some point become optically thick, there is very rigorous multiple scattering going on. Yeah? You can dump a lot of momentum into the wind, and that drives wind efficiencies. That is basically what is the momentum in the wind divided by the radiation field. Efficiency is larger than unity. When the winds become optically thick, eta, the efficiency, becomes larger than unity. And that provides what I call the kink in the mass loss rates. So if you have mass loss rate versus gamma, here you have your normal O stars. They follow some sort of Custer-Abbott and Klein relation, and you would think that for very massive stars you just extrapolate that, but then you're wrong. Because now, here at this transition point, the wind efficiency equals tau equals unity. You can show this analytically. That's a PowerPoint problem. That's not a real kink. This one is real. We need to boost the mass loss rates by a factor of a few. And you might think, oh, this is just detailed wind physics. What is the relevance of this for stellar evolution? It's massively important because that is what causes these very steep drops in the mass in these stellar evolutionary calculations. And that is also, if you plot it now in a Hertzsprung-Russell diagram, if you have a low mass, 100 solar mass star, it wants to inflate. But then it would not produce any ionizing radiation. The stars that we observe in 30 Doradus, they all have the same temperature in R136. But the stars have different masses. Some have 100, some have 200, some have 300. How is it possible that on the one hand, the star wants to inflate like crazy, and if it inflates a little bit here, then the 101 solar mass star is becoming a red supergiant. On the other hand, if you have strong mass loss rate, it wants to go expose the core. These two effects are both extremely sensitive to to the Ellington parameter. So to get everything at the same temperature, there's only one solution, and that's a vertical evolution. So that means we can keep the stars hot. These are 500, 400, 300, 200 solar mass models, and they all produce the same track. And they all fall onto the same track. They're all formidable sources of ionizing radiation. And stellar evolution is still poorly understood, and people always argue about, is it overshooting, is it rotation, is it binary, is it mass loss rate, what is it? But everybody always agrees that the most important parameter in stellar evolution is stellar mass. Well, actually, here, it's not the mass, it's the mass loss rate. Yeah? Because if it's 500, 400, 300, 200, it doesn't matter, but it's the rate that sets the evolution. And then again, in the classical Wolf-Rayet phase, you have a second phase where you have another vertical evolution. So that's a new framework that we have provided, and that's going to be very important for ionizing fluxes, especially helium-2 ionizing fluxes, because again, it all depends on the kink. It all depends on where the winds become optically thick and thin. So if you have helium-2 ionizing flux versus L/M ratio for different metallicities, what you can see is if you have a relatively low L/M, so a relatively low mass loss rate, you have huge amounts of helium-2, and then suddenly the wind becomes optically thick, and then you completely drop your ionizing helium-2 ionizing flux. Yeah? And this is not a factor 2 effect. Yeah? We're talking 10 to the 48, to 10 to the 40, we're talking a factor of 1 billion. Yeah? Now, people sometimes talk about factors of 2. I've actually seen people arguing about a factor 2. Then we have actually factors of 1 billion. Yeah? So we really need to understand the atmospheres of these stars, and that's what we're after. Just to say, the helium-2 continuum flux, of course, is very interesting from the optical depth of the wind, but the winds can also be leaving an imprint. If you have slower winds at low metallicity, you could potentially get narrower lines. So when you see helium-2 emission, it doesn't always mean nebular. It could also be a slow wind. In the last minute, I just want to say about chemical yields. They can provide us extra information. And in the most recent paper that we have submitted now, we're actually looking at low metallicity, very massive stars. And if you look at the sodium versus oxygen relation, and that is for globular clusters, an anti-correlation that could potentially be explained by these kind of models. I'm not going to claim that we know everything about the globular cluster story yet, but it looks that our models go in the right direction, and there's been no tweaking of the data or anything like that. So we go in the right direction with very massive stars. So very massive stars are fundamentally different. It's not just, when we talk about the IMF, it's not just what is the value of the IMF, where's the cutoff. The physics is totally different. Yeah? They're optically thick, and that means they do different things. They start to produce helium-2 emission that normal O stars don't produce. They have these huge amounts of nitrogen and sodium, aluminium, and so on, that are very different from normal massive stars. So that's basically what I wanted to say.
Very much, Yorick. We've got time for a couple of questions. Yep, Carla.
So thank you. It was a very interesting talk. So I wonder that about the chemical abundance pattern from these stars, because in this case we're exploring nitrogen, but what about the other elements? And besides this, how is, I know that there is a different, I don't know, how can I say, problems with different things, but what about the atomic data for these things? Because one thing is the yields for these stars, but the atomic data that you use in comparison, for example, with nebular studies, are well understood these atomic data that produce all these elements, or the base of all these elements?
I'm not entirely sure what you're asking. I think you asked two things. One was about patterns, yeah, and one about atomic data. For the atomic data in the mass loss calculations, we use Courage line lists for driving of the winds. Yeah. On the abundance patterns, I'm not saying that very massive stars produce all the elements. I'm just saying, I think for the nitrogen and for the sodium and so, they're important. But for instance, for carbon, probably not, because carbon is produced in helium burning phase. So if you want to understand the carbon, you need to go to the helium burning phase. So, yeah.
Yeah, one final question maybe.
So I know that you have some very well developed
models to do theoretical mass loss rates, but are we ever going to be able to reliably determine observational mass loss rates in the VMS regime?
I think the problem is worse in the O-star regime than in the VMS regime. So basically, I don't have, at this transition point, yeah, that is the slash stars, so these are O stars, they have an absorption line spectrum, and these are emission line stars. At this point, this holds, so we know the mass loss rate very accurately. And with accurate, I mean, we don't know exactly precisely, but we know it very accurately. It depends. The only assumption is that there's a radiation-driven wind, and whether it's clumped or it's porous or anything like that doesn't matter. Huh? So here, we are in very good shape. Here, there are uncertainties, because it depends on the prediction. But from the observations, you actually have electron scattering wings in the emission lines, and actually, you can get pretty good mass loss rates, pretty accurate. In the O-star regime is where the issues are. You have very tiny little lines, and there is much more uncertain.
Okay, I think we can leave it there, and thank Yorick once again. Next up, there's a slight switch in wavelengths, so we're going to have Anastasia Fialkov tell us about prospects for constraining the mass distribution of the first stars with 21 centimeter cosmology.
Thank you for having me here. It's great to give this talk. So it's on 21 centimeter cosmology, which is very high redshift probe, a bit hypothetical now. We don't have a detection yet, but many telescopes around the world are working on it, and there are prospects to go for the moon maybe in the future. So it's very interesting, I think, and the developing field. Yeah, let's see. What does it hold the, how do I? Okay. Okay, great. So we've heard several nice talks about JWST and about the discovery of galaxies at very high redshifts, redshift 14 and even maybe higher. But these are very bright galaxies, while deep in the epoch of ionization, while we believe that the majority of galaxies at those times are much deeper than JWST can see. So that's exciting, but it's not the whole end of the story. So on the complementary note, 21 centimeter cosmology, which is a measurement of the hyperfine splitting transition of neutral hydrogen, can offer a measurement of a statistical signal from the whole compilation of stars and galaxies existing all the way throughout cosmic dawn. As we define it in 21 centimeter cosmology, it's the epoch just beyond the epoch of ionization and before the dark ages when the first stars formed. So this signal would give us access to the whole invisible population of stars through indirect measurements, and it's very promising in my view. I'm very excited about it. The SK has started construction just this year. There are already several, two stations in the field, and signals from each individual stations were received, and the cross correlation was also achieved. So this is a low frequency array located in Australia, and it started working. It will take 5 more years for for first science data to arrive, though. But that's not the whole story. There are many other telescopes around the world that are already taking data for decades, providing upper limits that can constrain some of the interesting scenarios. So just to give you a brief overview of what we are looking at, so 21 centimeter signal is roughly broadly given by this. There are many different components that go into it. It's a kind of radiative transfer problem of low radio frequencies, photons. To the kind of zero order, it measures, of course, the ionization history. So XHI is neutral fraction here. But through radiative transfer, it's also sensitive to the background radiation in radio, which is CMB plus any radio emission we might have at high redshifts. It's sensitive to the gas temperature, which depends on the population of heating sources such as X-ray binaries. And it is also sensitive to the UV light in the Lyman band and ionizing photons as well. So it's the whole bunch of things, and every one of these components has different evolution across both time and fluctuating around the space, which contributes to a very rich signal that varies in time and space. But to the large degree, it is a measure of contrast between radio background and gas temperature. So green line minus divided by this yellow line in the presence of starlight, which couples this effective temperature of hydrogen to mass temperature. So we do need stars to see it. And then we do need contrast between radio background and gas temperature. And it fluctuates. I will not go to detail, but all the sources fluctuate differently with different effective lengths. So that's an output of our simulation. Just to give you an example, it's a very rich picture that evolves in space and time. And as sources evolve, also the signal will evolve. So in the past couple of years, we were interested to explore, can the signal that in principle will be measurable all the way from redshift 50 to 6 with this radio interferometry and radio signal experiments. So can it tell us anything about the first stars? And this is from a recent review by Klassen and Glover, where they show a compilation of initial mass functions for population 3 stars available in literature. We see that there is, and you know better than I do, that there is a very large uncertainty and variety in model predictions. So can we establish which one is true with 21 centimeter cosmology in the future? And a student of mine who unfortunately left the field done this very simple population synthesis study, which Rob Izzard is part of, so questions can be answered by him as well. So we used Robert's mint tables for 0 metallicity stars to create. So this is from NISA to add to pass them through stellar atmospherical plastic, creating this spectra of stars. And to give you for comparison, all previous studies in 21 centimeter cosmology were done with just black body spectra. Nobody looked at realistic spectra from stars at all. So we were the first to really use a realistic spectra, and this is a 0 metallicity as well, so it's very relevant to cosmic dawn studies. So we did it for very different mass stars and then compiled spectra for populations versus time for several initial mass functions. And this spectra are shown in the range of frequencies relevant for 21 centimeter cosmology. So starlight will create several impacts on 21 centimeter. It couples the spin temperature, so effective temperature of hydrogen, to gas temperature. It acts as feedback to star formation, suppressing subsequent star formation in small dark matter halos. And at those times, stars form in dark matter halos of 10 to the 6 solar masses, so much smaller than today. And it also, this starlight will heat up the gas, because at those times gas was very cold, so multiple scattering of lambda alpha photons will preheat the gas. So all these effects collectively contribute to 21 centimeter signatures by stars. And this is a sky averaged signal from 21 centimeter versus redshift. And this is a power spectrum at large scale of 4.1 co-moving megaparsec. So just by taking direct effect of starlight on 21 centimeter, we see that massive stars would have some signatures, because the massive stars would not have signatures, so they will all contribute to the same kind of profiles. But if the population of stars is low mass, we will have strong signals, and I can explain later why. So that's not the whole story, because population 3 will end their lives, evolve into population 2 stars through metal enrichment. And then they will also form X-ray binaries if there are binary stars that we expect to have many of them. So we did a parallel study with a postdoc of mine, Nina Sartorio, where we created, again, using the same, using binary C code of Robert, spectra for X-ray binaries for different IMFs as well. And of course, there is dependence. You get different balance between massive and low mass stars, and different luminosities for X-ray binaries. So here we see that low mass X-ray binaries are very inefficient in heating up the gas. This is spectra versus energy, while high mass and fiducial IMFs give us quite strong heating population. So this will affect 21 centimeter as well because it measures the contrast between gas and radio background. So we put that all together in 21 centimeter code that we have in the group. And overall, we explored 6 different IMFs here. So we have very like saltpeter-like in purple and very heavy, top heavy mass IMF in yellow, and different combinations in between. Top right shows different X-ray SEDs for each population. And the bottom panels show on the left the sky average 21 centimeter signal, and on the right the power spectra for each different IMF. So we have very strong signals when we vary IMF only, but we fix population 2 stars, population 2 X-ray binaries, and other properties of the code. So potentially there is a very strong signature over a very broad redshift range from 35 to 15 or so. But the question is, there are many uncertainties. So if we marginalize over them without, rather than fixing, can we still detect this IMF signatures? And in the study that we did, this is again the first ever done study. No one explored this before. So there are many uncertainties to include, but the ones we did marginalize over give very promising results. So if you marginalize over population 2 stars and ionization and so on, we get that for a fiducial IMF, which we here took to be flat, we can extract it from a global sky average experiment that is with the fiducial error bars and with a SK within a reasonable time. So that's very promising and a lot of field to explore further. I think no, I'm not done. So we all, as you all know, there are many uncertainties here that need to be tested in star formation and X-ray binary formation and evolution scenarios that we need to probe further and study further. But where we are now with 21 centimeter cosmology, there are some existing limits. So there are no reliable measurements, but there are limits from both interferometers. So this is HERA, which is a radio interferometer in South Africa. SARAS is a global signal experiment in India that provide upper limits. So specifically SARAS provides upper limit at redshift 25 to 15, very high redshift probe. SARAS at the moment provides limits at redshift 8 and 9, but they also have a high redshift experiment now on the way. So with these upper limits, we conducted this Bayesian analysis to infer parameters of population 2 and population 3 star formation efficiencies. And we get some very weak constraints. So they're very weak, but they are already constraints. So blue is the joint fit where we put together, so interferometer global signal experiment. We also used upper limits on the unresolved X-ray background from Chandra, which kind of gives us the upper limit. We cannot over-predict that, otherwise Chandra would have seen the sources. And we have a similar radio background from LWA. So putting everything together, we get a very weak constraint on population 3 stars and a bit stronger constraint on population 2. A more interesting constraint emerges for X-ray luminosity, actually. So our joint probability has constraints from 2 sides. From the very luminous side, it is constrained by Chandra. We cannot over-predict luminosity of high redshift population. But from the very weak X-ray luminosities, we are constrained already by 21 centimeter experiments. And so I'll stop here. Thank you.
Thank you so much, Anastasia. Questions? Yeah, Richard.
Thank you, very nice. Given the uncertainties that you showed, do you think the absorption signature, one of the arguments that people were very negative about the EDGES result was it didn't, the absorption didn't match their theoretical predictions. I know it's not been confirmed by the SARAS experiment, but do you think that the shape of the signal that, is sufficiently well understood that we would one day, see it and believe it, given the uncertainties that you showed?
So we're actually getting similar shape to what I just detected in some of our models, because if you put together several heating sources, so we had in the model a cosmic ray heating and X-ray heating, and in those cases, there is a competition between cooling and heating, and you do get flattened profiles. So in principle, we just don't include it in standard processing because there are already too many parameters. But in principle, we need to do that in the future.
Where is the FDP now?
Probably in the bunkers doing more, doing more experiments. They're not very well funded at the moment, unfortunately, in the US, as you know, and it has been always a very small team of just 2-3 people working at a time. EDGES is a very small experiment similar to Sarah, so like this one, but on the ground and square. It doesn't need many people to build the experiment, but it takes a lot to verify its kind of accuracy. So in Cambridge, we have an effort going on now called REACH, which is a similar grade experiment, but ground-based. And it's now taking data, so we're waiting to maybe hear about detections very soon. It's a much bigger group, so we're attacking it from all different directions.
Well, can I ask one quick question, please? So in your different flavors of the IMFs that, we eventually would like to test, do they have different sort of X-ray heating prescriptions baked in already? So is it like some sort of a circular effect where if you have more high mass stars, do you produce more high mass X-ray binaries, for example, that change your?
Yeah, exactly. That's what you see here, right? So this is X-ray SED from all of these IMFs. So purple one is salpeter. It doesn't have very many massive binaries, so you get overall very low kind of luminosity. So it all comes from population synthesis, binary C code, plus a kind of prescription to calculate X-ray luminosity.
Okay.
We also have other different heating mechanisms here, from shock heating and Lyman alpha heating and cooling by expansion.
Thank you. So if there's no further questions, let's thank Anastasia again. So we'll move on next from massive stars to massive black holes. We have Yuki Sobe, who's going to tell us about average nitrogen enhancement in high redshift broadline AGNs.
Yeah, thank you for introduction. Hi, I'm Yuki Sobe, postdoc in Cambridge. Today, I'd like to talk about nitrogen enhancement in the high redshift broadline AGN stack. Yeah, maybe there's no need to say, but I briefly explain the standard view of the local Innova evolution. The Innova O as a function of gas phase metallicity, and the local measurements are shown here. And as you can see, there is a low Innova phase in the low metallicity regime, which is dominated by primary enrichment from massive stars, dominant oxygen from the core collapse supernovae. And the high metallicity regime, we see the increase in Innova O due to the secondary enrichment from less massive stars during asymptotic giant branch phase. However, the JWST detected the nitrogen lines in the GNZ11 at ratio 11, and Alex nicely derived the Innova ratios here, and which is significantly higher than those local measurements. So its origin has actively been discussed. Also, interestingly, here the centronito plotted the abundance of the global cluster stars here, and which is similar at the high Innova ratios shown. Also, this line ratio of nitrogen 4, which is sensitive to the electron density, then that GNZ11 has a higher electron density than local galaxies. So these findings brought us new questions like whether there is any other high-redshift nitrogen galaxy, or what is the origin of nitrogen gas, or whether there's a link to dense star formation. To tackle these questions, we first look into the early release science data to search for additional nitrogen-rich galaxies. These ERS data are released immediately after the observations. Thanks to these ERS surveys, ERO, Sears, and GLASS, we could reprocess and compile 135 galaxies at a ratio 4:10. Here's a computation of the spectra. And in this sample, we search for the nitrogen-rich galaxies, and we eventually find 2 galaxies, one of which from GLASS, and then the other one is from Sears, at a ratio larger than 6. We derive ANOVA ratio from these UV emission lines, and we also carry out the ionization correction using a cloudy ionization models. And here's the result. Oh well, but yeah, please see the local relation here. But our results are shown here, which is significantly higher than those of local measurements and comparable to those measured at GNZ11. So we find that GNZ11 was not actually the only nitrogen-rich galaxy in the early universe. Then what is the origin? As in Yorik's talk, one possibility is to assume the CNO cycle in massive stars. This is a schematic view of the inner structure of massive stars, and in principle, the heavier alpha elements synthesized in the layers, and the outer layers can be ejected by stellar winds or something. And in the hydrogen burning shell, we can expect the CNO cycle, which enrich nitrogen with respect to carbon and oxygen. So this CNO cycle enriched gas will be ejected by stellar wind, then we'll see the nitrogen-rich gas in the hydrogen universe. Oh, terrible. and actually, if the nitrogen enrichment is occurred by the CNO cycle, then we will also expect the high nitrogen over carbon abundance. And here, please see here, is the composition of the CNO cycle, then which is higher than those of the quark option over here. And we also plot the local galaxies here. It's just actually less dependent on metallicity. It's just because the carbon is also a secondary element. And we plot our High Redshift galaxy measurements here, which is significantly higher than those of the local measurements and biased toward the composition of CNO cycle. So this high ANOVA ratio can serve as another evidence of CNO cycle process gas. And many researchers, discussing the contributors of early CNO cycle, not only Wolf-Rayet stars, very massive stars, as in Yorik's talk, but even the hypothetical supermassive stars. Some also assume the tidal reception events, which is the interaction of compact object like black hole to the massive stars, which can also strip the outer layers of stars into the ISM. And we plot these chemical evolution models into the ANOVA and COVO diagram and compared with observation here. And as you can see, these chemical evolution models nicely produce the observed CNO abundances. After the release of ARS data, many NeurSpec data have been arrived, like J's. Remarkably, in the data release 3, we have more than 2,000 sources at the ratio 0.513. And this is only a subset of the compilation of J spectra. And also, J has a deep field of 16 to 32 hours of the exposure time on average. Not only J's, there are many important programs like Excel's or Geo programs. So, thanks to these massive data and our passions, we see larger than 10 nitrogen galaxies at the ratio larger than 5. Then what can we learn from the ratios? Then from these sample size, we getting to notice that there can be a common feature in the nitrogen galaxies. For example, as you can see, we I summarize the Inova ratio as a function of electron density, and the nitrogen-rich galaxies are coming here, and it has the higher electron density than the local measurement shown here. Also, Harikaneto nicely showed that the size evolution of the redshift and the nitrogen-rich galaxies here have the compact morphology, even compared with the galaxies at similar redshift. So nitrogen-rich galaxy can be the dense and compact galaxies, even compared to the higher redshift galaxies. Not only that, some nitrogen-rich galaxies have AGN signatures. For example, not only the broad lines in the GS3073, also the hallucination lines. For example, GSD9 has a high the neon 5 emissions with a high hallucination energy of 97 electron volt. Of course, not all nitrogen-rich galaxies have this kind of AGN signatures, so it's really non-clear. So this raises a new question: is there any connection between nitrogen enhancement and AGN activity in high redshift? So we decided to explore the nitrogen abundance in the high redshift AGNs. We use the type 1 AGN selected from JACE, and it is selected by the H-alpha broad lines. And due to the coverage of null spec wavelengths, these type 1 AGNs are located at the redshift not less than 7. And we'd also like to cover the important emission lines in redshift UV. So we focus on this redshift range. In the same redshift range, we construct a type 2 AGNs from Shozeto. And we also construct the non-AGN sample, which is subtracting these two type 1 and type 2 AGN sample from the parent sample. And each sample has a some source numbers of 20, 18, and 665 sources, respectively. And here's the result, which is posted just last month. And the top one is a type 1 AGN, the type 2 AGN, and non-AGN. And as you can see here, only in type 1 AGN stack we see nitrogen 3. But the other one is not less significant. Using these emission lines, we derive the Inova ratio as a function of metallicity in the direct temperature method. And we see that type 1 AGNs have supersolar Inova ratios and comparable to the nitrogen-rich galaxies, while the type 2 AGN and non-AGN stacks are not very nitrogen-rich compared to many of the nitrogen-rich galaxies located here. We also see the Inova ratio as a function of electron density. This time we plotted all the singly ionized doublet. We see that type 1 AGN has not only nitrogen rich, but also high electron density values. And what can we, explain this link? And let's assume dense compact starbus as discussed in several papers. In such a dense star formation, some simulations expect the runaway merger. This is the merger tree of the stars, which can create the massive stars. Even supermassive stars, and also the interaction between the black hole and stars can also make the TDE, which can strip the nitrogen-rich gas. If stop here, we see the nitrogen-rich galaxies without aging activities, but such kind of galaxies may possibly be a minority, given that there is no nitrogen-3 in the non-aging stack. Also, importantly, this runaway merger can expect the formation of intermediate mass black hole. These massive seeds can easily grow into the supermassive black holes with sufficient accretion. And this kind of accretion disk, massive stars can still form. and contribute to the nitrogen enhancement. In this sense, we can say there is a synergy between the nitrogen enhancement and AGN activity. And kind of such kind of extreme nitrogen enhancement may take place in the only the central dense region of galaxies. Please see this result. This N/O ratios is derived from the UV nitrogen lines, which is higher than those of the nitrogen 2. It might be because the UV nitrogen lines have higher critical density than optical one. If such a stratified system is observed from the opening angle like here, we can possibly see the kind of night range type of AGNs. But this kind of night range feature can be less visible from a different side, which might be the reason why the type 2 AGN stack does not have significant night range 3. Yeah, here's a summary. Thank you.
Thank you very much, Yuki. Very exciting stuff. We've got time for a couple of questions. Maybe I can ask one. Oh, Chiaki.
So in your interpretation, where is oxygen, do you think? So the problem of nitrogen oxygen ratio is if you wait too much, quark-glup supernova produce a bunch of oxygen. So relative nitrogen oxygen quantitatively becomes low.
Yeah.
So in your story, where is the oxygen? How do you avoid this too much enhancement of oxygen in your scenario?
Yeah, that is also an important point. And yeah, it's okay to say when we assume the stellar winds from the very massive stars. But yeah, we also think about the bunch of oxygen from quark-glup supernovae. And some theoretical work predict that if we see this kind of compact and dense object, then the oxygen from a quark-glup supernovae will easily be expelled from such kind of compact system due to the high ejection, high explosion energies. So such kind of chemically differential wind can also be responsible for that kind of high innovation in such kind of dense compact objects.
Can I ask about when you showed the N/O versus, I think it was O/H for all the stacks? Yeah, this one. So there's still, I see still those galaxies in the very top left corner. Yeah, what is GNZ11 one of them?
These one? Or
yeah, these ones here with like
this,
extremely high N/O.
Sorry to not mentioning, but these abundance ratios are actually those of the global cluster stars.
Right.
Yeah. And yeah, this is only the stars from only one global clusters, but we also see that there is time deviation in the different global clusters. So maybe, but some global clusters have such kind of high nitrogen-rich stars. Yeah, this is the point.
Okay. So your AGN stack is kind of pushing us in the right direction towards the galaxy N/O measurements, the ones with the red highlight. Yeah, so a lot of them are consistent with the type 2
yes,
type 1 AGN.
Okay. Well, we have the lower limit of nitrogen over oxygen, so we can expect that. And yeah.
Cool. Any last question for Yuki? If not, let's thank Yuki one more time. Hey, so we now have 2 rapid fire flash talks about gravitational waves. So can Storm and Divya Jyoti, if you could make your way to the front, that would be great. So we'll start with you, Storm. Exploring the evolution of massive stars through gravitational wave observatories.
Yep, thank you. So, hi everyone, my name is Storm Collins. I'm a PhD student at the University of Glasgow, and I want to introduce gravitational waves as another way of probing these extreme stellar populations and probably complementary to these other kinds of methods that we've been talking about today. So to start off, I want to introduce our current gravitational wave catalog. So GWTC3, which is the collection of the binary black holes and other compact binary coalescences that we've detected over the LIGO, Virgo, Cagra 01, 02, and 03 observing runs has given us around 90 confident events, while we have about 200 more as of a couple of days ago from the ongoing fourth observing run that's been going for about 2 or so years. So from these events, we measure merging binary black holes that probably come from massive stars. And while we measure these at redshifts of around up to 1 or 1.5, these stars come from higher redshifts and turn into binary black holes as their final merger product. So these stars are typically thought to come from isolated binary evolution as one potential formation pathway, or alternatively finding each other in dense stellar environments such as globular clusters or nuclear star clusters. A lot of these evolutionary processes and how these black holes came to be so close and eventually merge for us to detect them, there's lots of uncertainties surrounding the astrophysics of the binary black hole progenitors. Despite this, we can detect certain properties of the black holes from the gravitational wave signal, so their masses, mass ratio, spins, and redshifts, and we can form a picture of their population properties as a whole. So to understand more about this, the astrophysics of our population, we want to compare the population to a population model. This can be based off of population synthesis, and we can investigate different formation scenarios, different environments such as the isolated binary evolution or dynamical cluster environments, and explore a range of formation metallicities, as well as specific stellar evolution processes such as mass transfer, supernova physics, and stellar winds. So in order to understand where the black holes that we're detecting come from, we can do Bayesian inference between our observed gravitational wave catalog and our population synthesis model. So here's some results from this type of investigation that I've done using GWTC3 events and a population model that considers 5 different formation channels, 3 of them from isolated binary evolution and 2 of them from dynamical formation channels. Within these channels, we also vary the natal spin of the black holes, and within the common envelope channel, the common envelope efficiency, so the efficiency that the common envelope is ejected with. The blue distribution is what we measure using our observations. So we find that black holes are born with low natal spins, less than 0.1, and high common envelope efficiencies, reeling beyond what our models consider at alpha CE of 5. We also find that our underlying population comes majority from the common envelope channel. So that's that panel on the left there, while we do have fractional contributions from other channels. And these are important to understand our population because we're actually more sensitive to the higher mass mergers that come from these observations. And so our detected population actually comes from a pretty equal mixture of these formation channels. We can also look at what our population, our measured population looks like in terms of our gravitational wave observables. So here I've plotted the distribution of chirp masses. So this is a chirp mass that we measure, reduced mass that we measure of our binary black holes, the mass ratio, effective in-spiral spin, and the redshift distribution. These colored lines represent the different formation channels that we consider and their fractional contribution from each, while the gray distribution is our total inferred population. And we compare this to the latest default models from LBK population analysis. So we can use this as a kind of astrophysical motivation to introduce new parametric models in our parametric analyses and see, for example, things like we have a contribution at high chirp masses from dynamical channels and a kind of more structure in the mass ratio distribution and higher spin contribution from our astrophysically informed analysis. So just to summarize, I've shown that we can use gravitational waves to infer some of the astrophysics of massive stars, and hopefully we can use this to continue learning about the different formation channels of the gravitational waves we observe. Thanks.
So no questions, but you can find our Flash Talk speakers after this. And then the final Flash Talk and also the final talk of the day is Divya Jyoti from Cardiff, who's going to tell us about extreme stellar populations also with gravitational waves.
Hi, everyone. So this is like an advertisement talk for the next generation gravitational wave observatories. Also, the two observatories that we are closely working with to finalize and solidify proposals include Cosmic Explorer in the US and Einstein Telescope in the Europe. So we are working on building a science case for funding these observatories, and we would very much like inputs from the larger astrophysical community on the kind of needs that they have or you all have for sort of the multi-messenger astronomy in the next 10 to 15 years. So I'll be giving a brief overview of the kind of things we can expect and why that may be exciting for the larger astrophysical community, not just gravitational waves. So just looking at some of the basics here, the current detectors that we have are at the scale of a few kilometer length arms. So LIGO 4 kilometer, and then we have Virgo and Kagra, which is 3 kilometer long arms, L-shaped interferometers. There are some planned upgrades for LIGO in the coming few years by the end of this decade, which would result in a sensitivity which would take us from the design to say something like which is called A sharp, and that would be about going from this blue line here to this purple one. So this would be about 5 times at the most sensitive frequency. But then we are talking about these two next generation detectors, which are Cosmic Explorer and Einstein Telescope. So Cosmic Explorer is planned to be just like LIGO in design, but the length of the arms is going to be 10 times. And Einstein Telescope is proposed to be a triangle with each side of the triangle as 10 kilometer length. And these two observatories are planned to have much better sensitivity, about an order of magnitude better than the current detectors that we have. So right with this sensitivity, right away we can see that the range of these detectors will increase by a lot in redshift. Also, on the frequency, we are so the plan is to extend the frequency band a little bit more on the lower side. So at the moment, we start with 20 hertz with the current detectors, but with these, we are planning to go as low as 5 hertz. So this would be beneficial because we can then probe even more massive sources, much more massive black hole binaries. As Storm mentioned, we've had about 100 detections till GWTC3, and we are expecting about at least a few order of magnitude more in the next gen. So this is the overview plot of what all can be done. So here, just before I delve into the details. I would just compare with the various generations. So this green curve is kind of the redshift envelope of detection. So on the y-axis is redshift, x is total mass of the binary. And we see that at the moment we are dealing with barely detectable sources at 1 redshift. But as we improve, we can go up to redshifts of 10 and even much, much higher redshifts with the Cosmic Explorer observatory. So this is a picture showing the capabilities of Cosmic Explorer. So you have your normal black holes sitting here, which is between about 1 to 10 redshift here. These will have signal to noise ratio of about 100, a few hundred. Then you have the neutron stars here again in the detectable range with signal to noise ratios of up to detectable 200. And in between you have the NSBH. But also we have some very interesting things going on at high redshift. So we have POP3 black holes, which are expected or theorized to form directly from POP3 stars. This could be very exciting discovery that we could have with the Cosmic Explorer. And of course, this is purely theoretical, but we could also detect some black hole seeds or primordial black holes with this kind of explorer. And so these would be the key objectives for the larger astrophysics community, which would benefit from these observatories.
Thank you. All right, so that brings us to the end of our specialist discussion meeting. I think we've had a wide variety of amazing science and amazing models and amazing theory that we've seen today. Hopefully that helps bring all of these communities that tend to work in sort of isolated corners together, because we need, as Elizabeth said, galaxies are made up of stars. You can't just be a galactic astronomer without being a stellar astronomer in the modern day and age. So I just wanted to say thank you again to all the speakers and all the attendees. Thank you for coming, and then let's give ourselves a round of applause and have some tea.